Let me know if that connects.
Hello, it's nice to be back for the next NuttX International Workshop. Aline and Alan.
Hello, guys.
Alison is somewhere in the building, still trying to sort out a few organizatoric issues. And we are really happy to be here in Japan, in the Sony office. We have quite a big crowd. Nice to see so many people. Nice to see finally that this happened. This event happened in Japan. We were planning to have it in 2020, but COVID came and things didn't really go as planned. So I think that since we are running a bit late, it's time for us to hurry, and I will do a bit of house cleaning and tell people that are attending here how the event will happen, and then we will start with the first presentation. So first of all, welcome to our small event here in Japan. Welcome everybody online. And for the event for the day, we will have sessions until lunch. Then we have lunchtime for attendees on their own. There is a canteen here in the building. We can also go outside. During the lunch, we will also run demos. You have a few demos over there. We have SoraQ. We have a robot that our colleague will present. And after lunch, we will come back and continue sessions until evening. When these sessions end, we will organize dinner here in the Sony building, 4th floor. So that's the schedule for today. After the dinner, please return the badges to us. You will get the badges tomorrow again. That being said, we have a few boards from a few sponsors, and we also have organized a NuttX Presence workshop that will happen tomorrow morning. We have 25 boards for 25 people that want to wake up quite early and participate to the workshop. So if you're interested to work with this presence board tomorrow morning, contact us during lunchtime, and we will add you to the list and provide you the board for tomorrow. If you are not interested in the workshop, please come tomorrow from 10 after the workshop ends. That way you get a bit more time to prepare your slides or time to sleep. That being said, we will proceed with the first presentation. Tomek, can you show please the schedule?
I don't know.
My view, there are 7 seconds delay. Mm-hmm.
Yeah, it's there.
So like every year, we have a status report because it's good to know where we are in the entire community and what we can improve. So my name is Alin Gerpelea. I'm doing the releases for the NuttX project. I'm the chair of the NuttX project, and now I'm I think 7-8 years contributing to NuttX. It's a lovely community and I really like it. So without further ado, we will look at the NuttX, at the RTOS landscape. We will look at our project, our community, and our license status. For the real-time operating system landscape, I was inspired by Kate from Zephyr to look how projects are doing, how many contributors they have, and when were the projects started, what licenses they have. So last year I presented something similar. If you compare the numbers between this year and last year, you will see that there are a few increases and decreases. One of the biggest changes is that the Azure RTOS has been archived, so there is no contribution there happening. And also CMSIS has 0 contributors for the past month. If we look at the size of the projects, NuttX is the second with 135 contributions in the last month, following Zephyr, which has 942 contributions. The others are also active, and each one of them has a specific scope. Also, if we look at the licenses for those real-time operating systems, we can see that most of them are Apache 2.0 like NuttX. Also, something to keep in mind is the fact that we have Minute, which is also an Apache project, and maybe there are interesting things that we can exchange with them. Looking from the SBOM perspective, and I will come back to the SBOM a bit later. And last time I started a discussion last year. This year I will follow up with what we see that is a requirement from the industry, a requirement from the government, and also what are our next steps if we want to follow that. So looking again at the real-time operating systems, we have the RTOS, free RTOS, which provides an SBOM under MIT license with the SPDX identifier. We also have Minute, which provides a plain text license header, and they have SBOM provided, and also Zephyr has an SPDX identifier, and they provide SBOM, and they are the pilots on the SBOM. I attended a talk from Kate, and she was presenting the status of the SBOM for Zephyr. Quite interesting talk, and we should follow their example. That is my personal take on that. For the project perspective, the project started in the 90s. The project has been created by Gregory Nutt. The picture is on the right. Thank you, Greg. If you hear us or see us, we would love to see you in the speakers lounge. Then it launched as a first release in 2007 under the BSD license. Greg donated the project in 2019 to the Apache Software Foundation when we started the incubation. And then we graduated as a top project in 2022. Since then, we are mostly focused on growth. We got a few companies engaged. We got more developers. The board grew a bit, and we are looking for standardization. If you have more ideas for the future, we would really like to have them and grow the project to the direction that it needs to grow. The characteristics of NuttX are portability, availability, scalability from 8 to 64-bit, AMP and SMP support, compatibility, and also Edge AI support since 2 years ago. The project is mature. It has a constant coding style. We are trying to maintain that coding style to quite high standards. It has an active developer community, like you saw, and it has an open license. The main license for the project is Apache 2.0. The requirements to run NuttX are quite low. It requires a low medium microcontroller or microprocessor. It requires no MMU, though if you have an MMU is even better. It works from 8 to 64-bit. It requires all 8 kilobytes of RAM as a minimum and 16 kilobytes of flash. The project started for 8-bit MCUs, and it is real-time from scratch. Also, it favorizes low power consumption, and for this presence board, we managed to achieve quite impressive numbers in the power consumption figure due to both the hardware and the software. For the different versions that happened since last year when we had this conference and up to date, we have new architectures that have been added to the project, and also we have new boards that have been added to the project. I tried to get a snapshot of what has been added. I will not read them all, it's too much. So please go through this screen after the event. Also, we have to keep in mind that the NuttX real-time operating system is available on many platforms, from MIPS, Extensa, OpenRISC, RISC-V, x86, x86-64, ARM, ARM64, Z80, which is nowadays hard to find due to the discontinuation of the hardware, and AVR. Last time I counted, and I counted quite a while ago, there was support for over 300 boards. I guess that now we are close to 350 or even more. I promise that for next year, I will do a new counting of the boards, and I will provide the update number with the real figures. NuttX is used in many products. Sony used it in digital audio recorders. It has been used in activity trackers, printers, drones, safety devices. It has forks in Tizen RT and Google Ara. Is used by Sony, Xiaomi, Samsung, Fitbit, Motorola Mobility, Haltian, 3D Robotics, Verge Aero, and many, many others. And maybe something that you missed, or maybe you show on LinkedIn, we are really proud to have NuttX also on the moon. Sony sent the smallest robot in Japan historical astronomers history, a small robot, the Sora Q. We have it here in the conference. We have not clone, sibling. Yeah, I'm sorry, I don't.
toy version, please.
Yes, but we have the real board, so the real device there. So if, in case you missed the news, you find the whole article at the bottom of the page. We are really proud to be on the moon with NuttX and Sony that made this possible. Here we have the project activity. As we see, the project has ups and downs, but it always has a continuous development. There were a few peaks when new features have been added. Now we are in a phase where bug fixes and board support is added for more platforms, enabling more people and more devices to use NuttX. For the release statistic, the latest release has been in April. It was a bug fix release, 12.5.1. And the next major release planned is 12.6.0 planned for June. So quite soon, at the end of the month, we will branch it out. Our release schedule, the committed release schedule, is every 3 months unless something happens. If we have a bug that we discover and it's a major bug, we will always do an intermediary release before 3 months pass. Each release increases the code with around 800 push requests and around 150,000 lines of code. So quite a big shout out to the community working on this. It is an active project, and it's quite fun to work with. From the licenses perspective, I want to remind you that we have added build barriers, and you have to select the license when you build your own code. By default, only the Apache license is supposed to be used. Please remember that this feature is still work in progress, and the only licenses that are completely shielded in this moment are GPL licenses due to their nature. For all the other licenses, you have to check manually because we still have licenses that are ignored when this flag is set. I think that this kind of issue will be corrected completely after we have the SBOM support, because we will be able to check what we select in the menu for the kconfig and what we get in the final build as licenses. So that will be probably the big step up for us to fix this work, which is quite tedious. And every time when a commit comes, we have to check it. For the full licenses, there is a license file in the source code, as you can see. Please open it when you build a product and check all the licenses that may be added to the project. As a recap, the main license for the project is Apache. We have other licenses in the code: BSD, MIT, GPL, EPL, ISC, and you should always check the license file for details. When the SBOM will be implemented, all those licenses will be reflected in the final build SBOM, and it will be way easier to check. From the community perspective, we have over 100 contributors. Here you have just a few picked from the GitHub. There is no ranking in this slide. The intention was not to show a ranking. The idea was to show people that contributed at various periods of time. As you can see, Gregory was extremely active until 2020, and a big shout out for that commitment. And also we have other people like myself that started quite late, and we have way less contributions that Gregory, which build the whole core of the RTOS. But we are taking the legacy further. All the authors that have signed CLA are in the authors file. You can check it. Please check if you are a contributor that you have signed the CLA and your name is in the authors file. Another aspect of the community is support. Our main communication channel is the Apache mailing list, dev at nuttx.apache.org. If you have any questions, if you have any suggestions, please send them to the mailing list, and we will all work on either guiding you or taking in consideration your suggestion. Thank you very much. I think that I am on time. We have a few minutes for Q&A, and then we will proceed to the next presentation. Are there any questions? Thank you very much. The next presentation is from Xiaomi Vela.
Hello, I'm Xiaoxiang, a software architect from Xiaomi Vena team. Today, I will talk to you four topics. First is introduction to Xiaomi Vena. Second, the relationship between Xiaomi Vena and NuttX. Third, the contribution from Xiaomi Vena to the NuttX community in the past year. Last, future outlook of Xiaomi Vena. Okay, let's start the first topic. First, let's take a look at the overall situation of the Xiaomi IoT platform. Xiaomi has been investing in AIoT and smart hardware since 2014. Our platform has always been globally leading in terms of scale and categories. As of March this year, the number of smart devices connected to our platform has exceeded 699 million, and our platform has over 84 million users. According to the last date, our user is 1.8 times higher than the second platform. Our platform not only has a larger number of devices, but also has a wide coverage. We will achieve full coverage of smart living. For example, Xiaomi TV has been the sales champion in China for 4 consecutive years, and our audio and fitness tracker products has already been industry leader. Currently, there are over 9,000 developments from various companies, including Panasonic, IKEA, and Philips. There are 3 characteristics of IoT devices. First, they are numerous. The current low number of IoT devices has been reached 10 or even hundreds of billion. Secondly, they are diverse. Different IoT devices vary greatly in terms of functionality, performance, and resources. Lastly, there is ecological isolation. Different IoT devices use vastly different protocols, operating system, middleware, so application developer must write program for each type or even each device. All of these factors has led to extreme fragmentation of IoT devices, making standardization and scanning difficult. Xiaomi Vena is an IoT operating system built on the open source real-time operating system NuttX. Vena provides a unified software platform for various IoT hardware and through which components and standardized software stack framework. It connects fragment IoT operation scenario. Vena was created to solve the problem of IoT fragmentation, which leads to low software reuse, high cost, and low quality. By active building, Vena enables multiple product categories to reuse technical engineering capabilities, and for each product category, it has larger resource input than its competitor, ultimately leading to a leading experience and cost advantage in long-term competition. In the fourth phase, we will mainly focus on the 2 core areas of consumer IoT, smart homes, and wearable devices. We have already completed support for product categories such as smart home appliance, smart speaker, smart sensor, and smart watch. In the future, we plan to gradually support Vena on other smart devices, ultimately covering more low-Android devices from Xiaomi. In the initial stage of the project, we conduct an all-common lightweight operating system in the industry. In the end, we chose to develop Vena OS kernel based on open source real-time operating system NuttX. This diagram represents the architecture of our entire system, with the bottom left column being the Vena kernel developed in collaboration with the NuttX community. NuttX is responsible for providing basic kernel services and is known for its good compatibility with Linux and its lightweight nature. It's for this reason that Vena is very suitable as a replacement for Linux. After switching from Linux to Vena for our own products, hardware cost can be significantly reduced. We have co-developed this part with the NuttX community and are the largest contribute to the community. On top of the kernel, we have developed unified services, frameworks, and tools to provide a modular solution for different IoT applications. This solution captures the common requirement of wearable IoT application and provides the company compatibility required by the device. By using VNA, both device and chip manufacturer can significantly reduce their development cost. Over the past 3 years, we have accumulated mature landing experience and have been applied in hundreds of smart wearable and smart home products, as well as over 20 million devices. Last year, we have also launched several heavyweight products, such as the Mi Band 8 Pro, Mi Watch S3, Xiaoai Kid Speak, and the Mi Smart Home Panel. Last, we will continue to deep integration with the Android system and further improve the device experience of the smartwatch and smartphone. We have been involved in the NuttX project since 2017. In 2019, Xiaomi invited NuttX founder Greg to Xiaomi for a 2-day technical exchange. During these 2 days, we have officially decided to become a strategic partner with NuttX. Together, we will strive to promote NuttX globally and bring it to China so that all developers and device manufacturers can enjoy the technology benefit from NuttX. We suggested contributing NuttX to the Apache Foundation at that time. The next day, Greg left a message in the NuttX community saying that he had learned a lot about the Xiaomi IoT platform and deeply understood why a unified system like NuttX is needed for IoT ecosystem. He expressed his willingness to guide Xiaomi and join the Apache Foundation. So, in the same year, NuttX was promoted to join the Apache Foundation. And finally, in 2022, NuttX successfully graduated from Apache and became a top-level project. Last November, the first Xiaomi VNA Open Source Summit was held in Beijing. Alan, the secretary and developer of the NuttX community, giving a presentation on that event. In the past few years, we have also subscribed to the concept of openness, mutual benefit, and work together with the global community to build through open source. Since 2017, we have been actively involved in the NuttX community, adhering to open source collaboration. Today, we have 3 PLC members and 4 committers. In the past year, we contribute more than half of the code modification, making us the largest contributor to the community. This year's workshop, we have prepared 8 presentations summarizing our major contribution to NuttX over the past year, which include VNA emulator introduction, new debug analysis tools, audio I/O and API messaging improvement, CMake build system, V4L2 decoding and encoding framework, network subsystem improvement, graphic and input subsystem enhancement, x64 ARC improvement. Please join this workshop session for the detail. Finally, let's look into the future. Xiaomi VNA and NuttX are joined together, committed to building the best IoT platform, and Android Linux companion RTOS cover more categories of devices and constantly involve our capability, complete cross-core, cross-device, heterogeneous interconnection capability, open and win-win developers ecosystem. This year, we will launch 2 new categories products, TWS earphone and smart speaker with screen. In the next 2 years, VNA-based smartwatch, car ECU, and CyberDog will be released. AMP framework is used as a basic communication mechanism between cores or VM drivers such as socket, console, provide a high-level using view for application and services. There are 3 cases to cover for VLAN AMP hardware link between SoC in a board. For example, the SPI physical link is used between 2 SoC. Shared memory between VM and a hypervisor. In this case, audio will be used for underlying communication. The basic communication is still the memory shared between the 2 VM. Shared memory between CPU core and a chipset. For example, in the scenario of communication between AP core and the CP, DSP, SP, these cores are integrated in a single chipset. Since they share DDR, the communication between them also uses shared memory. Binder is a communication mechanism widely used in the Android system. Therefore, we implemented Binder on VLAN to better support communication and interoperability with Android. We are based on the existing Android Binder RPC and implemented an RPC session object based on the optimization socket. In the Linux kernel, we implemented the optimized socket, and through this socket, we can communicate with VLAN OS using Binder. The advanced offloading framework, such as audio, graphic, connectivity, and sensor, are all based on optimized socket and Binder CPC to hide the complexity and diversity of the transport layer. Since the inception of VLAN, we have been actively preparing to open source it. In the past few years, we have primarily concentrated on building internal open source projects for Xiaomi, assisting numerous teams in enhancing their research and developing efficiency, and optimize product experience and quality. Through this process, we have amassed a wealth of technological expertise, and we are eager to share this accomplishment with our industrial partner. Therefore, our upcoming plan is to open source VLAN to promote overall industrial efficiency. That's all. Thanks.
One. We are live right now.
Hello, everybody. We are back from Japan with the NuttX compliance. My name is Alin Jerpelea. I'm working together with the community. Sorry, we have a sound issue.
You are not sharing your screen, Alin?
Yes, I am.
No, it's not YouTube.
Okay, let me check. Can you see the screen now?
Yes, it's alive.
Yes. So I will restart then. Hello again from here, from Japan. We will proceed with the next presentation. My name is Alin Jerpelea. I'm working together with the NuttX community as both project management committee and the chair of the project. I'm doing the releases for the project, and I usually feel that there are some needs from the compliance perspective, especially when doing releases. So I started this topic last year, proposing that we implement the SPDX headers and we correct a few issues regarding compliance. And this year I'm following up with the updates from mostly the legal side and what the governments are asking. Not only us, the NuttX community, but they are legal requirements that will soon become mandatory. So first of all, what is SPDX? SPDX is a standard, an open standard for communicating the software bill of materials, including provenance, license, security, and other related information. SPDX reduces redundant work by providing common formats for organizations and communities to share important data, thereby streamlining and improving compliance, security, and dependability. The standard number you can find in my slide. If you want to go through the standard, is quite detailed and quite an interesting read if you're interested in the standard itself. In the past slide, I mentioned software bill of material. What is a software bill of material? A software bill of material, or short form SBOM, is a list of all open source and third-party components present in a code base. We need the SBOM. The need of SBOM is driven by several factors that include ensuring the software transparency, managing open source software and third-party dependencies, identification and mitigation of security vulnerabilities, and also compliance with legal and regulatory requirements. There are several SBOM types, but we as a community should, in my opinion, focus mostly on the source SBOM, which will detail which files are shared as source, and the build SBOM, which will detail which files are included in the final target for each build. So for the NuttX project, I've been looking into implementing those, and it is a work in progress. Hopefully, the next version of NuttX, NuttX 13, will have support, or at least partial support for them. Looking from a legislative side, in Europe, we have the CRA, Cyber Resilience Act, which has been promoted by the European Parliament on the March 12th. And the CRA uses the software bill of materials to describe, record, and monitor product security. Therefore, a formal document outlining the CRA compliance requirements and describing all the SBOM specific requirements will soon appear. The CRA doesn't have yet all the policies on how to be applied, so we are looking on the publication. On the other hand, the German government published the technical guideline for the cyber resilience requirements for manufacturer and products, where they define the software bill of materials as a machine processable file containing supply chain relationship and details of the components used in the software product. It supports automated process of information on software components. This covered both so-called primary component and the used third-party component. So, in simple words, it covers the open source part and the third-party part. The level of detail for the SBOM is also added in the SBOM. I will not go into details. You have the link with the full document. It's quite long, and it goes quite into detail what is needed for an SBOM. Also, if we look at another country, we have UK, which has a response call for views on the Software Resilience Act, and it is also quite an interesting read. I will not read the text. You can read it yourself. The link in the bottom of the page will take you to that document. I will share the slide. Those are quite long documents. Please read them if you're interested into this side of compliance, not only as a product, but also compliance from the open source perspective. And then we have the other continent that adopted something similar. We have the USA, and they have the executive summary, which says the dramatic increase of cyber compromises over the past years, specifically the software supply chain, prompted intense scrutiny of measures to strengthen the resilience of supply chain for software used through government and critical structures. So they are basically doing the same thing. NSA is doing the same thing. They are proposing an SBOM as a part of the supply chain risk management. You will, I'm sorry for the text that cannot be read in the presentation. I will fix it before uploading the slides. You have also the link to the full document. It is quite a long document, and it is hard to read it during the conference due to the time that we have available. What we are proposing for the NuttX SBOM roadmap, or what I'm proposing, because in this moment I'm the person doing the releases, is to implement the SPDX identifier. I pushed the first commit implementing SPDX. There has been a really good comment from the Apache Foundation and other members. Now we have a way forward, and I will proceed sending the other 28,000 patches that or patches for 28,000 files that will correct and implement the SPDX. After we have the SPDX, we will investigate the format that will be used for NuttX, what are the available tools that can be added to our build environment, and then integrate the SBOM generation directly into the build environment. So the expected time plan from my side is probably the next 6 months to have a full implementation. Hopefully things will work as I'm planning. If you have any questions, I would be happy to answer them. Otherwise, I thank you very much for this session, and I hope that we will find a lot of time for discussion later when the other continents will have some clarification on the SBOM from their side, and also after the European Union publishes the policies, how to apply the CRA. Are there any questions from the room? Are there any questions online? Please.
Thank you for the presentation. And what versions of SPDX will you target to produce as SBOM?
In this moment, I'm considering the SPDX 2.4 Lite. For a real-time operating system like NuttX, I think that the Lite version is something that we can easily use. While in the future, if the widely adopted standard will be SPDX 3, we will probably migrate. I also spoke with Kate, and Zephyr uses SPDX 2. So maybe it's better to be aligned with the other real-time operating systems instead of trying to do something cutting edge, which will take time to be adopted. But that is my personal opinion.
Thank
you. Please, Fukuchi-san.
Perhaps the same kind of questions. My understanding, you are targeting the SBOM producing like Zephyr project. So you are targeting the same as the SBOM over the Zephyr produce. Is that correct?
Everybody that produces an SBOM will produce something similar to what Zephyr produces, because that is the SBOM structure. Mm. What we are targeting is to have a source SBOM and a build SBOM. So both of them should be provided by NuttX just to be compliant. And also the generation of the build SBOM will help us fix the licenses. Because in the SBOM, you can see that you selected, so at build time, you will select that you want to have only Apache licenses. And then in the SBOM, you see that you have a few files that have a different license. Then you as a developer can go into the code and fix that. So it will help us find the licenses that in this moment are slipping in between. It's too many files with too many licenses to manually assess it. And this tool will basically help us fix that and also fix compliance. Because in that case, when you select Apache and another license, you will be sure that only that will be in your product. So for a company, I believe that for a company, this will be a great opportunity for picking NuttX, because the licenses are already true to what we declare. So we correct the licenses.
So the background of my question is that in the marketplace, the two major real-time OS, the Zephyr and NuttX, I believe. And so if Zephyr produce some kind of SBOM, so perhaps people expect the same one as Zephyr. So my question is which it is better to produce same kind of SBOM as Zephyr.
Yes.
The Zephyr is the de facto for the real-time OS.
We produce the same type.
Same type.
Same type,
yes,
but the content cannot be the same because they have different files and they have different SHA for the files. So yes, that is the standard, and we are targeting that. It is actually a standard from OpenChain.
And so I think we should say that it is better to say that we can produce the SBOM as Zephyr does. It is a good message to the market.
Like that, or we can say that we produce an SBOM that is SPDX compatible, and Zephyr produces an SBOM that is SPDX compatible. I didn't mention there is another standard called CycloneDX, and from my knowledge, there are tools that can convert from one standard to another. So if a company is using CycloneDX and we produce the SBOM in SPDX standard, the tool will be able to convert to CycloneDX so that that company can ingest the SBOM. If we see in the future any kind of requirement to have CycloneDX, maybe we can incorporate the tool into our tree. But in this moment, it is way too far. We are just starting to add the SPDX headers as a first step, and that will be a really long step.
Thank you.
You're welcome. Thank you for the question. Do we have other questions or questions online? Nothing on YouTube. Okay. Thank you very much, Tomek. Please put the agenda and we follow with the next presentation.
Hello everyone, I'm Xu Xin from Xiaomi Vela. I'm very grateful to be a part of today's online workshop. Today, I would like to share with you the work we have been doing on upgrading NuttX build system to CMake over the past year. As of now, the CMake build system has been in use internally at Xiaomi Vela and has provided a very positive development experience. We have also been updating these features and bug fixes within the community proactively. Okay, let's start this sharing. Today's topic will include following 4 parts. First, I'll give you some background on the build system upgrades. This will include the problems we have encountered when compiling and building before. Afterwards, I will review the evolution of NuttX build system during the upgrade process. This part will include what we have done and provide a simple example to compare the differences from before and after the upgrade. Later, I'll focus on the benefits and value that CMake build bring to our project. I believe these benefits will bring great confidence to our build system. The last part, we will discuss the future work directions and plans. Okay, let's move on to the background. In the feedback collected from the development process, we have identified several key areas where our current build system is falling short. Let me outline these points and their implications. Our first major point of feedback concerns the speed of compilation. Users have found that build execution is slower than what's ideal. This slowdown can significantly impact development efficiency, especially in large projects. Moreover, our system currently lacks robust support for parallel compilation when working with multiple configurations. Another area of concern is the behavior of incremental builds. The feedback indicates that there are anomalies and unexpected in how incremental compile. This can lead to inconsistencies or errors, undermining the reliability of build process and potentially requiring full rebuilds more frequently than should be necessary. The cleanup process for intermediate artifacts has also been identified as an issue. Not fully clean up these intermediate files can lead to potential errors in subsequent builds. Ensuring a cleaning workspace is crucial for the predictable build outcomes. Lastly, the current systems lack the flexibility to compile a single module or target independently. This feature would allow the developers to focus on the specific part of the project they are working on, significantly speeding up the developer test cycle by not having to recompile the entire project for small changes. Addressing these issues is about enhancing the overall developer experience, making our build system more reliable, efficiency. Okay, let's check out how other projects are dealing with these issues. The same problems and requirements are prevalent in various large-scale projects. During the evolution process, most early large-scale projects will choose to switch to more modern build tools and enhance the compilation system. As can be seen from the following table, in the Atos field, many projects we are familiar with have experienced the upgrade in their build systems. More modern build tools can help us solve most of the above problems. This also proves that this is a necessary choice for everyone. Next, I will introduce the evolution of NuttX CMake build process. Initially, in 2019, the earliest attempts at CMake build originate from the PX4 community. It is the experience of these pioneers that provide a data support for construction optimization. Then, committer protobits from the NuttX community officially submit a migration pull request to the NuttX system. He optimized the PX4 solution and formed the prototype of the current CMake build base. In 2022, Archer from the Vela team restarted the work on CMake. He refined many CMake modules and made improvements. Over the past year, the NuttX community and the Vela team has worked together to implement more ARC support and app supporting on CMake, enhance the more CMake build features. In the future, we will continue to try more convenient build tool integrations and more product usage. This part is about what we do. We will discuss significant upgrade in our transition from a Makefile-based build system to CMake within NuttX. First up, we have greatly enhanced our toolset by encapsulating a host of CMake modules. This mimics the functionality of our original tools, while also providing more convenience and modernized core approach with the build process. Furthermore, we have restructured the build target level by breaking down applications and libraries into independent CMake targets. we have not only improved the granularity of the build configurations, but also refined control over dependencies. Lastly, we have improved our support for third-party libraries with native CMake scripts. Their integrations into NuttX build system is now more straightforward. Below, I will make a simple example to directly reflect the changes in the CMake build system. That's how we add an application to NuttX using CMake. As we can see, first, in terms of directory structure, we need to add a CMake script, which is a CMake list.txt to the original application build directory, which is the directory where the makefile is located. In this simple example, we add a simple hello and shell built-in application. In the original build system, as shown on the left, we need to follow a template, which starts with include apps make defs and ends with include application.mk. This template will help us supplement the key compilation stages, compilation targets, and various macro settings. We can fill in the present variables, for example, prog name, main source, success. In CMake, we have refined the serial template into a function called NuttX add applications. The usage and prototype of the function are introduced in the CMake module file. It will automatically create a CMake compilation target for us and complete the built-in register. Variables such as success and prog name are replaced by function parameters. As shown on the right, adding an application to a CMake build is reduced to a single function call. We can also wrap CMake macros in our own CMake scripts to further simplify the code. Another example is how to port a library to new CMake build. I have used the simple unit test library CUnit as an example. For external libraries that support CMake scripts themselves, we can port them in 3 different ways. The first way is to treat it as a general external code and use general port method, which is to collect the source files and header files we need, and then call the NuttX add library function in CMake to create a target for the external library, and then fill the source property for the CMake target. Our built-in implementation will link the final application library to the NuttX ELF outcome. The second way is to use CMake module NuttX add external library, which directly adds the CMake script of the external library to the current build context, and reuse its own target and property configurations. At the same time, adding the definitions and include directories compiled by NuttX and achieve the same goal. The last way is use the CMake built-in module external project. We can compile the external library into a static library as a separate compilation process that is completely independent of the current compilation. The current compilation toolchain and the compilation options are passed to this independent compilation process through this module. Finally, the static library product is used by import that target to link to the NuttX ELF file. The choice of which way to use depends on the situation. We need to evaluate the complexity of the external library. Next, I will introduce the benefits of CMake upgrade, which is also the main part. First of all, the most important benefit is the direct improvement of compilation speed. In our test, CMake builds are twice as fast as original build system when using the makefile generator. This speed is even faster when using the Ninja generator. In a complex single configuration scenario in Xiaomi Vela, we use the CMake build to optimize a configuration that takes more than 10 minutes to 3. This will greatly improve the efficiency in CI verification, package, and local development. The second advantage is that now we can support parallel out-of-tree build. This will further improve the compilation speed by using parallel multiple configuration compile on the top of direct compilation acceleration. This will be very useful when using multiple configuration product. At the same time, the compile out of tree will ensure that our source tree is not polluted. That's completely solving the disclean residue problem. The third advantage is automatically handling the dependency. Compared to the current weak dependency implementation, the new CMake build will be more reliable for incremental compilation. Fourth, support independent compilation of single module targets. Implement independent verification of single module and import and export of library. The final advantage is excellent cross-platform capabilities and more friendly development experience. After above introduction, let's plan our future work directions together. In the initial stage, we will continue to improve the currently missing features. CMake current coverage capabilities are still not perfect compared to the original makefile base. In the next stage, I plan to complete the documentation related to the CMake build. Documentations and guidance are also what we are currently lacking. More investment is needed here. Finally, in the future, we plan to integrate universal build tools to make it easier for users to use. We will achieve these goals in order. Finally, there is a special part. We would like to extend our deepest gratitude to the following individuals for their invaluable contribution and support. Thank you for your code contribution and review support. Your effort has been instrumental in driving the success of our project. Thank you for your dedication and hard work. Thank you all.
one.
Okay, so here we have a question from Yu Ping Xiao in the YouTube, and he's asking, I saw some libs under apps not having cmake.list.txt. So here we have a question from. Does it mean we have not finished all porting? In the YouTube, and he's asking, I saw some libs under apps not having cmake.list.txt. So here we have a question. Okay, thank you, Shushin. Yes, he confirmed it needs some improvement yet to include all the libraries. Okay, so I'll come back to you, Thomas. Okay, thank you.
So thank you for waiting. So and thank you very much for coming to Sony Osaka City in Tokyo. And I'm very happy to be here. And today I'm talking about the status updates for NuttX 6.4 on QM plus hypervisors. And about me, maybe it will take this time is short. So I did develop so many products before, so including Linux Workman and Android-based Workman, and then we this as you know, NuttX-based audio recorder as well as headphones. And recently, I'm doing feasibility studies and doing some presentation at the Embedded Linux conference as well as the NuttX International Workshop. So this is today's agenda. So first, let me introduce the last activity at NuttX 2023. And then I quickly review the hypervisor and the KVM, which you might know. And then I will talk about the NuttX target comparisons, including emulator and simulator. And then I talk about how we can run a Bravio sound so with and without USB audio device. This might the reason why we use these two types of devices configurations. You will see the reason later. And then I will show you how we can use performance so with NuttX to trace guest OS. And finally, I will show you them videos. So this is a slide from NuttX 2023 last year. So happened in Brazil. So I visited Brazil for first time, and I talked about this slides in Brazil. And at the time, I introduced how I implemented Bravio MMI.net as well as Bravio block devices. And this is the right side. You can see here how the network device can be configured. For example, this is not this is NAT-based configurations, and these are bridge-based configurations. And I showed some demonstration, including with and without KVM. But at this time, I didn't not so much about hypervisor and KVM. So today, I'd like to show more internal. So what is a hypervisor? So maybe you might know so hypervisor is a type of computer software, and we can create and run the virtual machines. And so you can present guest OS as a virtual operating system. But very interesting is unlike emulator, so the guest execute most instruction on their native hardware. So this might be very good, how to say, good for testing because most of the interactions and runs are without emulation, so very quick. But sometimes if we access the device server, it changes to a hypervisor, and so some overhead happens actually. And this is a KVM. So what a KVM is. So as you might know, so KVM is open source virtualization module in the NuttX and allows the Linux as a function hypervisor. But it needs a hardware extension, virtualization extension. And for example, x86 and ARM and PowerPC supports these extensions. So we can run, for example, NuttX as a KVM guest, and these guest OS can actually run on this virtual CPU, but this virtual CPU is mapped via hypervisor, and to run on actual CPU, so physical CPU. And there is a, you might know, NuttX has some target configurations. So maybe most of you are using actual real board. For example, Subway6 squared is a NXP i.MX series, and presence, as you know, and ESP32. This is extensor architectures, and of course, you might use some STM32 related boards. And other targets you might not know, but there is some targets like simulator and QEMU. So QEMU was divided into two categories. So one is without hypervisor, and one is with hypervisor. So so simulator, you can use both x86 64 architecture as well as ARM64 architecture. And with QEMU, you can, for example, there's these configurations, but with hypervisors, only two targets is currently available. So one is QEMU Intel 64. This was maybe added 3 or 4 years ago, but very limited. And last year, I added this QEMU with 8A to test our some devices, including networking and block devices. And these are differences between each target. So real board is, of course, we need a real board. So we need to buy, or we need a, but and we cannot use multiple NuttX instances on the board. So you need to buy. if you want to run multiple NuttX targets, you need to buy more boards. But simulator and the QEMU, both QEMU targets, so we don't need actual real targets. And of course, we can use multiple instances. Yeah. But there's some differences between from real boards. For example, simulator, as you might not know, booting and context switch and interrupt and signal handling, these internal code is little different from actual real target, real board. And as you might know, QEMU without the hypervisor uses a so-called TCG. This is a tiny code generator is used. So for example, if you run a RISC-V related RISC-V based NuttX code on x86 machine, this QEMU, this tiny code generated transcode, so on the fly. So this RISC-V code onto our target machines. So this, in this case, x86, and so this will be our overhead and not so fast. But it depends on our target or hardware configurations. Yeah, actually, Cortex M3 is maybe very fast to emulate, but maybe Cortex A9 with MMU and maybe slower than actual board. And with hypervisors, yeah, as I said, interactions with hypervisor happens so when accessing actual hardware, but most of the code does run very quickly, and so there's no translation. And last year I introduced a BART.io, and QEMU with that hypervisor might use BART.io drivers, but some targets, for example, as you know, ESP32, these this target can use same drivers on both real board and QEMU, and yeah, actually other this Subway6 squad is also same, so we can use the same target drivers on both real board and QEMU. And with hypervisors, we usually use BAT-IO-based drivers because there is no full driver emulation at this time. So most users will use BAT-IO-based drivers. So this is BAT-IO support status in the latest QEMU, so QEMU 9.0.0. So last year, I also showed this slide, but at that time, QEMU version was 7.2 or something. And after that, QEMU added some features, so like audio. Yeah, this audio feature has finally merged in QEMU 8.2.0, I think. And yeah, actually, most of BAT-IO types are supported the latest QEMU, but some of devices are still not supported yet. And this is an update since NuttX 2023. So I did this kind of sent a pull request and finally merged. So first I added the BAT-IO sound, and this driver was contributed by Xiaomi. So I again thanks for Xiaomi that they contributed this driver to our community, but there is no configuration to test this BAT-IO sound driver. So that's why I added this configuration to both on an RB bird. So this is a RISC-V target, and this is a QEMU with 8A, so 64 targets. And at the time, I tested with this, Raspberry Pi 3B Plus, and it works. And then I bought a new, not so new, but Raspberry Pi 4B. But soon I found that it crashed actually, and I investigated why it crashed, and finally found that this GIC V2, Generic Interrupt Controller version 2, so detection scheme code is, there is a bug in this detection code. So I finally fixed and finally works on Raspberry Pi 4B as well. And then I added an NX recorder to record the audio. So yeah, actually I first tested only the playback. Then I added the recorder to record the audio signal. And then I said QEMU version was changed from 7.2 and 9.0.0, so which it was released on April this year. This is the hypervisor support, and actually when I talked last year, I didn't too much about these topics. And yeah, actually, the QEMU 64 configurations, originally we use GIC version 3, but we need to use the GIC version 2 for hypervisors. This is why, for example, so Raspberry 3B Plus is has a proper controller. Raspberry Pi 4B uses a GIC V2, and this MacBook Pro uses Apple interrupt controller. But this is very important. GIC V2 emulation is not only supported in QEMU Plus hypervisors. So that's why we don't use a GIC V3 for hypervisors environment. And also, I need to change to use HBC hypervisor core for PSCI. PSCI is used to boot secondary processors. As we talked before, NuttX supports SMP, so symmetrical multiprocessing. So if we need to boot the secondary processors on hypervisors environment, so we need to use a PSC, this PSC interface. But to call a PSCI, we need to use the HBC instruction. So this code stack shows how secondary processor boots, and you can see this HBC code instruction. And Also, we need to start year one. So year one is exception level one. This shows us means OS run OS, and instead of year two, because nested virtualization is currently not supported. So that's why we need to use we don't need to use this option for QEMU. And this is running as a wireless sound without USB audio. So we can use these configurations, and you can set these parameters options for QEMU. So for Raspberry Pi 3B and 4B. So you just you need to add you need to specify audio depth as answer, and but as you can see, this is I executed error command to see which devices card is available. But unfortunately, original Raspberry Pi does not support audio input. So that's why I need to add I need to use a USB audio device. This will be covered in next slide. And as for MacBook Pro, so we need to specify a core audio instead of Arthur. But this backend only supports playback. So yeah, so we cannot use our audio input with MacBook Pro at this time. Yeah, this is with USB audio device. You can use the same configurations, and you can use, for example, this is audio device which I use. In this case, we need to, the card is detected like this. So as you can see, a record minus L and A prime minus L. So you can see both card is detected. So that's why this means that we can use audio input if we use this kind of USB audio device. And for example, this audio device has multiple input port, so we need to change capture source. For example, this is a change to line, and also maybe we need to change the capture volume as well. This is a performance comparison with hypervisor. I think I showed that maybe same slides before last year, but I changed my environment. So I'm using the latest NuttX, so which was released on this April. And we actually we changed the web server version and Mac OS version, and also I changed the compiler version as well. And these are numbers for so first is get prime. This is to find the prime number to check performance, just CPU performance. Maybe so this is with a hypervisor, and this is with hypervisor, and maybe around 4 or 5 or 6 times is faster. So with hypervisors, and this is IPER, so network performance numbers, and so one is without hypervisor, and targets is client mode and server mode, and yeah, actually, I say speed is not so high just compared to get prime, because it needs to access actual hardware, and in this case, there is hypervisors overhead happens, and this is a very interesting approach, not approach, but I found that this path command is very useful for to debug the hypervisors as well. So maybe you might know path command. This is a performance analysis tool, and there is a PMU, as you might know, and but you can use collect guest OS information as well. And for example, this shows a code stack, and and when I run IPAP-C, so, and with KVM KVM top commands. And as you can see, there is a bottlenecks in memcopy and checksum. So maybe we need to optimize these functions to improve more performance. So when sending and receiving packets, yeah. But as I noted, obtaining the code graph is on the guest OS is still not supported. But maybe future there is some patches for only Intel architectures. But maybe soon, I believe, 64 architecture, some guys will contribute to support this feature. And so finally, I show demo videos, and so I use this environment, so Raspberry Pi 4B plus audio device, and so guest OS, as I said, on the latest NuttX release, and I change the config schedule TQS Y because original upstream code you do not use a schedule TQS, but if we check such a call stack, timer interrupt, it's very annoying to show call stack. And I prepared two kind of scenarios. First one is just IPOF, and one is NX recorder and NX player. Okay, and change to let me change. And okay, let me. Okay, GT. Oh, loopback. So which? Oh, loopback audio. It's okay. Oh, I forgot to check loopback. And use some map. It's okay.
Yes.
Okay. Oh. Anyway, let me try to Perhaps there's no sound online, but let me try. And this is. So right one side, we use this side shows a parf command and then starts as QEMU. Maybe it's small font, sorry. And but there's no activities on right side because the first one is without hypervisors, so we cannot detect guest OS. And then just sending a packet, and maybe speed is around 43 megabps, and then change your with hypervisors and start just changing directly to KVM. Yeah, you can see here some activities on with Spark command. Yeah. And then, this is SMP applications. And then run our iParf. So you can see it almost the same code stacks, and you can mem copy and actually, so that is bottlenecks for we can find. So this is the first demo video, and then this is the second demo video. And actually I work IO top command to see actual IO activities. And so first, adding, so mounting a device, and then start recording, I think. So maybe, sorry, small font, but you will see these activities. Yeah, maybe soon start our audio recording. Yeah, you can see it. This is our write activity. So currently, you can also see some fast access control. And so actually, audio recording is working, and file is created. And then, yeah, actually stop recording, and then drop the cache. So before starting the next player, because so with caching, we cannot see any audio read. So then that next player. Yeah, actually, the sound is hearing from my MacBook, and you can see here actually read operation is happening on host devices. Yes. So that's all. So thank you for watching.
Thank you very much. Can we take questions?
You have any questions?
Yes.
Yes, please.
If you can go back on the slides when you had the comparison between different
different types.
Yes,
Mm-hmm.
and performance. You mentioned that you are testing now on the latest version of NuttX with the latest compiler. Do you have those numbers for a previous version of NuttX with previous compiler versions?
So maybe you're talking about this,
Yes.
right?
Yes.
Yes, actually, I have the numbers in previous workshop, but at that time, yeah, actually, the code base was very old, and so as I explained in previous workshop, my original driver was not so optimized, and then Xiaomi people developed a new framework for Bad.io driver just for networking, and then improved much for networking. But maybe, for example, so get prime. This is, I think, this shows only so CPU's performance, not for networking or such performance. So maybe these numbers, I guess, it's almost same, but this number is different. Yeah. So depends on the which driver and which framework we are using. Yeah.
I see. I think that this kind of measurement would be really good if we can test with the same toolchain and the Ubuntu version every NuttX release to see if we have a performance regression.
Yeah.
So it would be really useful to have it on the release as a testing phase.
Yeah, I think so. And actually, I found that so with hypervisor's performance is slightly dropped after I upgrade the macOS version. So maybe I'm not sure if why the performance is degraded after updating my macOS, but maybe we need to investigate more. Yeah.
Also, maybe it's interesting to do the same check for the toolchain, different toolchain versions, because then we can find the regression in the toolchain, if any.
Yeah, I think so.
So I suggest that we open thread on the mailing list, and then we start collecting data. I guess that will help both us for the releases and also the other members from the community to track different issues with specific releases. Thank you very much. Very nice presentation. Okay. We have time for one more question.
I have a question about this network configuration performance. So right now, you use kind of network stuff in NuttX source code, right?
Of course.
And there is one more good architecture is existing in NuttX named UserSock. You know?
Yes.
So
I know.
yeah,
I know.
how do you if you do some this kind of performance or analysis by using the UserSock, what do you plan to do that? For example, you will need to implement UserSock just for kind of the host OS stuff use, for example. What do you think?
I think the user SOC, as you know, is for example, as you know, we are using user SOC for the Wi-Fi, so because Wi-Fi device has its own network stack inside, and yeah, actually we use we can I measured some performance with presence plus Wi-Fi before, but it might be not difficult, but maybe for example, the Wi-Fi is very complicated. So, for example, we need to prepare the access point as well, and it yeah, actually might be so when not well. Yeah, we need how to say if we need measure the numbers, we need to use a very closed room for yeah to check the speed, I think. So it might be more difficult, I think. But just for thinking about the user SOC, of course, yeah, we can use the user SOC on simulator, and we use, but just for maybe looking back, I think. So I'm not sure if this performance measurement is useful or not. Yeah.
Yeah, because I thought this approach is very good for kind of the managing the performance on the NuttX implementation. So users also the part of the NuttX. So
yes.
how to say kernel side of the user SOC should be measure this kind of way to keep the performance is good.
Yeah.
So
I agree with you. Yeah, of course. Yeah, but we need how to say as I said, we need to have the testing environment we prepare. Yeah.
Okay.
And one, yeah, please.
Thank you. I have a question about this. Thank you for a great presentation. It's very insightful. My question is because once we use Vertio, we need the Vertio from driver to work in the guest OS, right?
Yes, you're right.
At present, I see you have implemented some device driver. Are there any other device driver implemented in the NuttX, such as network or web device or something like user input?
Yeah, actually, as I sorry, as I sorry, let me go back more slide. Yeah. So last year, I talked at this right, and first I implement Bata network driver, and then I implement the Bata block driver, and then Xiaomi people improved so they applied a new Bata framework, and I think they implemented as far as I know. Maybe they implement input device and some kind of devices. And then, so last year, so they implemented the battery sound driver. So, but as I said in this slide, yeah, sorry, yeah, maybe. Oh, sorry. Actually, yeah, sorry. Actually, so battery driver, sound driver is implemented by, yeah, contributed by Xiaomi. Yeah. But there is no testing environment, and so and of course there we could not use hypervisors with battery sound driver. So that's why I created this kind of public test to check the actual the battery sound driver test driver, so with and without hypervisors. please.
Thank you for your talk. This time you talk about business. But there are plans for NuttX to provide hypervisor or virtualized host function.
NuttX provides virtualization function?
Yes, for the virtualization host function. Yes, not this.
So you are talking about NuttX will support the hypervisor function? Okay, but in my, I think, yeah, actually, creating a hypervisor is might be not so easy. But yeah, of course, in some cases might be easy. But if we support, for example, March processor and MMU, and yeah, actually many CPU features, and of course 64 and Intel architecture, and yeah, maybe we need to re-implement such a so scheduler and hardware resource management in hypervisor. So we need to re-implement it. So this might not so useful for NuttX. Yeah.
My question is about I found Zen hypervisor.
Yeah, Zen.
They are implementing the non-zero and non-D
Yeah.
with Zephyr. So
Oh, really?
it's a very small footprint provide virtualization Zephyr method, the hypervisor and Zephyr as driver OS. So also Android is now using Kubernetes for automotive version. So it is a new development for RTOS.
Okay. Thank you for your thank you such a good information. Yeah, redirect it. Yeah, check. Yeah, thank you.
Do we have any other questions from the room? Alan, do we have questions from the internet? In that case, thank you very much, Masayuki-san.
Thank you.
Very nice presentation. And we are going forward with the next presentation. should appear.
Finally, welcome to my presentation. My name is Peter. I'm from Sony in Lund, and I'm happy to see that there was some interest in connectivity from this presentation. Welcome to my presentation. My name is Peter. I'm from see that there was some interest in connectivity from this. Welcome to my presentation. My name is Peter. I'm from
One.
Here we go again. Hope this works better this time. My name is Peter, and I'm from Sony in Lund, and I will talk about connectivity and various protocols. Here we go again. Hope this works better this time. My name is Peter, and I'm from Sony in Lund, and I will talk about connectivity and various protocols. Here we go again. Hope this
Let's try again. We had a few technical difficulties here in the room. Peter, please start.
Okay, so we are back online. I hope we are rid of all the feedback loops by now. We continue with the context of my experiences that I'm going to share with you, and that was to provide wireless connectivity for sensor networks. Why is that not updating? Oh, there you go. It's for low power devices that can run using power harvesting. We can accept low data rates, but we do need two-way communications for actuators, firmware updates, and stuff like that.
Security is, of course, imperative when we talk about modern communication of any reliable source these days. We also need cloud interoperability because devices reporting data should report it to some meaningful standardized endpoint, and AWS IoT is pretty much a de facto standard for such things. And all of this in combination means that we need some sort of IP connectivity. And to recap, this one is slow. There we go. To recap, energy requirements for radio communication, they typically depend on how much output power you need, which is a function of the range you need. The frequency plays some role in this, especially with vegetation, antennas, environment for the radio, your electronics, and the amount of data transmitted and received. And it's a known fact that many radio technologies spend more energy when the radio is listening than when actually transmitting. We'll get back to that later. Then there is overhead related to secure communication, and there are a few properties that you typically want to have when you communicate. Maybe confidentiality, that no one can eavesdrop your communication. That is more or less for free because you can do encryption without adding to the message sizes. To have integrity checks, you need something like message authentication code or integrity code, which is going to be 32 bits or more. If you go for digital signatures, you are in the range of 64 bytes and much more for RSA signatures. If you're going to do key exchange, we will spend at least 3 round trips for an authenticated key exchange, and the payload of those messages will depend on the size of your keys and your cryptographic schemes. So that brings to the question, why not just use a modem together with AWS IoT? For instance, the Sony Altair modem has pretty good power profiles, but the handshakes for TLS sessions to Amazon is not super IoT friendly. The chains there will spend like 6K bytes for the certificate chains alone. A device cannot sleep indefinitely and maintain a TLS session to Amazon. If you are absent for more than 15 minutes from Amazon, you will have to do a new handshake, and at the time we did this work, Amazon did not support the abbreviated TLS session resumptions. Looking at the LTE side for Cat M1, the TX power is most likely much greater than 100 milliamps. There are some nice power saving features in Cat M1. You can have extended DRX cycles, which means that the device does not need to be listening every 1.28 seconds, which is standard in LTE. Disconnection is a bit of an issue for a device sending small amount of data because it is network that allows when the device can stop listening to completely disconnect the network. And that depends on the network operator settings. It can be several tens of seconds. So for a super short transmission, you have an enormous overhead just waiting to be disconnected. A new feature, I think it's in release 14, is called release assistance indication. And there the UE can, or the modem can indicate that it wishes to be immediately disconnected. And then you can cut that down to maybe 5 seconds or so. But it's still a bit of an overhead for a short transmission. So instead of
using LTE communication, we can then venture into short-range radio communication. And one of the dominant one is the 802.15.4 packet radio, which is available at the 2.4 gigahertz band or 868 sub-gigahertz. Here the TX power is going to be much lower, like 10 milliamps or so. The link bitrate at 2.4 gigahertz is 256 kilobits, and that sounds good, but it's we will see later that it's a bit of an optimistic figure. To send IP packages over this bearer, we need the 6LoWPAN to fragment and assembly IP packages. Since the link is now limited, we can think of extending it using mesh network technologies. And then we need to solve the routing in our mesh network, where we can resort to the RPL or Ripple routing protocol, which is available in two flavors. You can either have only the root node with knowledge to do downward routing, or you can store routing tables at each node, in which case all nodes can do downward routing. And then routing brings back to the radio on listening, and there is an amendment called E of 802.15.4, which allows scheduling so that even a routing node can go to sleep. And there are two major approaches to that, either a protocol called six-top or autonomous scheduling called Orchestra. Security on 802.15.4, according to IEEE, is based on AES with symmetric encryption and or MAC. To distribute keys for the link layer, there is an IETF protocol called CoGP, which in turn rely on security protocols, OS Core for REST security on CoAP, or Lake for doing a full authenticated key exchange. And since this is quite a few components, we looked into existing implementations for this 6-tish stack, and one of them is OpenBSN, and the other major one is called Contiki, which have support for many Nordic semiconductor chipsets and also other platforms. But Contiki is not really a versatile operating system due to the internal structures for the callback interface, threading model, etc. So what we did, we integrated the two subsystems running the TISH stack on Contiki on an NRF board, together with Espressence using the user space socket abstraction, which allowed us to connect the board using UART. We've also tried this on the NRF53 series, but here we can actually run the Zephyr on the application CPU, so we don't need to have different SOCs to run both of the systems. And in that case, we have slip over the open AMP shared memory in Zephyr, which is similar to how you would run the thread stack on the 53 board. So waiting for this one to come up. I think we need to have the picture here.
You actually talk on your picture.
Yes. Okay, so we ended up with something looking like this. We have sensor nodes that will run a board with either the 52 series and NuttX presence, or we run on the 53 series with Zephyr, and they connect over the short-range radio to a border gateway, which consists of another board running short-range radio plus an instance of AWS Greengrass. And there we do need to do a little bit of a protocol conversion because the connections to the left is more suitable to use UDP-based protocols versus Amazon requires TLS and MQTT, but that we can do in a conversion with a component called MQTT-SN, which is the UDP version of MQTT. So for the conclusions of this, we can see that both the 2.4 and sub-GHz can offer good link range. In optimal line of sight conditions, we can reach kilometer of range. However, in vegetation environments, the 2.4 is super restricted. You can easily be down to tens of meters if you are in crop for agricultural use cases. Here, then the mesh network can, of course, increase the range, and with the standard 1:17 schedule, we can have a duty cycling that allows devices to sleep for 95% of the time. The link bandwidth here with this scheduling then is probably in the range of 3 kilobits, less in larger networks because the scheduling does not account for aggregated traffics from nodes in the sub-tree. And with a radio at 10 milliamps and 95% sleep cycles, we are pretty confident that we can have a device that can run using energy harvesting. So looking at possible future integrations to have this more native into NuttX, we can look at the involved components here. There is support for 802.15.4 in NuttX, as I understand, but not for the TISH amendment. 6LoWPAN is already in NuttX. There is no RPL, and there is no scheduling, and there is no JP. And then the last item I put is the spinel, which is sort of the host control interface that is used by OpenThread to communicate between an application processor and a network processor or radio control processor. So I hope that can bring some inspiration for the community for continued work in this area, because I think that low power communication is pretty important for IoT applications. That's about it from me for today. Are there any questions?
Thank you, Peter. Quite nice presentation regarding the application of communication for IoT. And I especially liked your last slide. So if I'm allowed a question.
Yes.
Are there any plans to go deeper than just analyzing? Are there any plans on actually contributing something to the NuttX projects regarding this IoT communication?
I think the work with the user space socket implementation that can onboard the TISH network stack similar to the Wi-Fi, that is probably feasible. I mean, the work is done. I think it's just a matter of packaging and formal approval and things like that to do that. But then there are other possible work items that you can also think of.
Thank you. We have another question from the room.
It's more like a comment, not a question. First, that Contiki MG OS already includes all the RPL routing code, and it is very mature and it works. So we can get inspiration from that.
Well, I would say that it works. To say that it's mature, not so sure. But you can definitely get the implementation, and for the actual protocol part that is the over-wire signaling, I would say that it's probably as close as the IETF specs that you can get, because they usually try things out in that platform before it gets standardized by IETF.
And the other is to achieve time-slotted channel hopping. This requires really tight timing and synchronization. So we will need some sort of hardware abstraction layers to support different radios that are like these discrete radios, like external chips like the CC1101. But we also need to support system on chips like the EFR32 from Silicon Labs. So we need to design some kind of hardware abstraction layers that supports this tightly timing of the time-slotted channel hopping. It is possible to do. I just raised the flag because it is not as simple as we might expect, but I am sure we can do it.
If you look at the IEEE specification, I believe that they have the sort of host control interface that will cover most of those topics. Then it's a matter of whether you want to implement it that way. The Contiki implementation does not follow the IETF interface at all. Yeah. They have their own way of doing it, more like callbacks for the different platforms. But it should be doable. I'm not sure if anyone has actually done it by the book that way. I don't know any other implementations of this rather than the OpenVSN and the Contiki. And it could be mentioned that there is a prototype integration of OpenVSN running in the Riot OS as a process. So we have the entire stack of the OpenVSN with the running into OpenVSN. I never got it to work on the 802 series, and apparently there was something wrong with the version of the 52 board that I was using, because I was involved in conversation with the Riot community, but we never got it to work. But that was also a sort of an interesting encapsulation to get the network stack packaged and running on your platform. Probably not the most efficient way to do it.
Many details.
Yeah.
Thank you.
Thank you very much. Do we have other questions?
Yeah, can you please read about the new audio? I think the audio from YouTube not good.
Read where?
From Tomek. What's the maximum size of mesh network and how it can be extended when the limit is reached?
Okay, so the question is, what is the maximum size?
Yeah, size
of the mesh network, and how can it be reached?
And how it can extend it when the limit is reached. It's possible to route between different networks.
Between different mesh networks. Yeah, you could, if you consider that to be like a form of border routing, because eventually you will need to route your traffic from your network to external internet or maybe another mesh network. So that should be possible. For the maximum size, I think the theoretical size is thousands of nodes. But when we do, we haven't, of course, built a network that's size, but we have ran network simulators that can evaluate performance for a large number of nodes. And what we can see is that the signaling involved for the nodes to synchronize, to be scheduled, and also to exchange the routing information, that part is becoming more and more bottlenecked when you add hundreds of nodes. Also very much depending on the topology of your network. If you have a very optimal geographic placement of your nodes, you will have one performance. But if you have an unlucky topology and also switch on the nodes in an unlucky order, the network would have to be rebuilt in order to find the optimal routes. And when you reach more than 500 nodes, that is becoming very unstable according to our simulations. But we think that is also a matter of your density. How many nodes per area do you really need? I mean, if we can have hundreds of nodes and we can have a link range of hundreds of meters, you will have a substantial area coverage already there.
Second question. Did you study or read or try it, the sidewalk from Amazon?
No, we have not in detail evaluated the Amazon sidewalk, but we intended this to be as much as possible infrastructure-less. That is, that we were thinking of a deployment of a network that can be locally managed by harvesting and mesh technology, and then at some point we will have some sort of an unconstrained border gateway that could be maybe even non-terrestrial for cases where there is no connectivity available in your deployment site.
Thank you.
Thank you very much. If there are no other questions, I would like to thank you very much for the talk, and let's proceed to the next one.
Hello everyone, this is Yi Changrong from the VENA team at Xiaomi. I'm very happy to be able to participate in this year's NuttX Online Workshop. I joined the VENA team in July of 2022. 2 years have passed, and today I will present on the topic of NuttX graphic and input subsystem enhancement overview. In my presentation, I will talk about some of the enhancements that have made to the NuttX graphic and input subsystem in the past 2 years. Here comes the agenda, which is divided into 4 parts. The Nitto Visual version 9 upgrade, driver framework enhancement, device driver enhancement, then the needed products and future work on graphic and input subsystem. Let's start the Nitto Visual version 9 upgrade. Nitto Visual version 9.1 is officially released on March 20 of 2024. We have participated in the development of many features in Nitto Visual version 9, including all the development work related to NuttX. Then we upgraded the porting layer of the Nitto Visual in NuttX application from version 8.3 to version 9.1 in April. Let's take a look at the main new features of Nitto Visual version 9. Firstly, the runtime display color format adjustment with RGB 888 support. Secondly, better parallel rendering architecture. Thirdly, SIMD support for software rendering, including Neon and MVE. The next feature is built-in display and touch driver, including SDL, Linux Firm Buffer, NuttX LCD, and touch drivers. Then, vector graphics is supported via SoftVG and VGNet GPU. The last feature is image decoder refactor and cache management, supporting aligning, stretching, or tiling the image source if the width is larger or smaller. The features like SIMD support, vector graphics, image decoder refactor, and cache management are mainly developed by the VENA team. The Little Visual upgrade has brought many benefits, and the future upgrade will be more convenient and easier to maintain for NuttX. As we can see from the diagram on the right, in the past, in order to support Little Visual, NuttX needed to maintain two folders, lvconfig and port, for Little Visual adaptation. Little Visual version 9 moves all the porting work internally, so NuttX does not need to maintain this work, and only need to maintain kconfig and makefile. In addition, we add some new features in the porting layer of NuttX. Firstly, use libuv to support the pool mode of frame buffer and the input device, which can save a lot of power consumption for a low power system. Then use NuttX heap management for Little Visual image cache module, which can fully utilize the advantages of NuttX. Finally, integrate Little Visual profiling mechanism with NuttX interface, which makes the profiling data more accurate. After introducing the Little Visual version 9 upgrade, we will continue to introduce the driver framework enhancement. There are many tool enhancements in the past years I would like to share. One is the vsync optimization, and another one is the MIPI DSI framework. Firstly, in order to better match the vsync signal with the timing of join, pool mode has been added to the frame buffer driver framework. With the implementation of Little Visual pool mode mentioned earlier, UI rendering timing will be more accurate. Then, I'd like to introduce another optimization named vsync buffer queue. Usually, the render timing of the application is driven by vsync signal. However, if the running time of a frame exceeds 16 milliseconds, the frame cannot be displayed on the screen in the next cycle. And in the case of MIPI DSI LCD, the transmission time for a frame is generally less than 16 milliseconds. So we can take advantage of this situation to increase rendering time. The implementation of the vsync buffer queue is very simple. During the initialization of the frame buffer driver, a frame buffer queue will be created. And after a frame is done, it ends the frame buffer queue. When LCD controller finishes transferring a frame, the frame will be decoded. At last, the track timing for application rendering changes from vsync signal to querying whether there is an idle buffer in the buffer queue. The vsync buffer queue can effectively improve frame rates and reduce frame drops. This is the frame rate improvement effect we obtained from vsync buffer queue on our product. As you can see from the chart, each scrolling scene has an average improvement of 3 to 4 FPS. Another important enhancement on driver framework is the MIPI DSI framework, which is implemented by Xiaomi miWare team. In the past, there was no MIPI driver framework on NuttX. For MIPI LCD, both the display and the control functions had to be implemented by vendor themselves in LCD controller driver. Each vendor needs to implement its own set of MIPI drivers, which brings a lot of repetitive work. MIPI DSI driver framework aims to decouple MIPI DSI panel driver from the LCD driver. Through the MIPI DSI subsystem, LCD panel control driver can be decoupled from the vendor SDK and realize a universal driver. Also, MIPI DSI subsystem supports air control operation in user space, which can be used to quickly light up a new LCD. In this chapter, we will introduce the device driver enhancement in NuttX graphic and input subsystem, which is mainly to support emulator subsystem, including QEMU and Goldfish environment. In order to better support simulation of graphic applications, we add a firm buffer device driver and input device driver based on virtual I/O spec. The virtual I/O GPU driver will get the display information from QEMU backend, like the X resolution and Y resolution. Then create the firm buffer for graphic application. The driver will send a flash command to QEMU through the virtual I/O transport layer to update the firm buffer. In the input driver, the input events defined by virtual I/O follow the NuttX event definition, including event type, event code, event value, which is different of NuttX input subsystem. The virtual I/O input driver will pass the NuttX input event and translate it into NuttX touchscreen event or mouse event or the keyboard event. Then send it to the up layer. This video is a little visual machine learning example running on a QEMU environment. We can see that it can properly receive input events and display correctly. In addition to QEMU, NuttX currently also supports the Goldfish emulator. So, we implemented the firm buffer driver and the input driver based on the Goldfish virtual device protocol. Basically, similar to the virtual I/O driver, we query the display information in the Goldfish firm buffer driver, then allot the firm buffer, and display the buffer through the Goldfish protocol. In Goldfish, the events of the input subsystem also follow the NuttX event framework, and the transport layer is changed from virtual I/O to Goldfish platform bus. This video is a watch application running on Goldfish emulator. You can see that the UI is very smooth and consistent with the real device. Another important driver enhancement is the U input driver, which can be used to simulate any input event in user space. It will receive simulated touch and key events, and then forward these events to the application layer. Also, it supports inter-core communication by API message, which means you can run simulated application in another CPU core. In addition, a monkey tool is added for stress test. The monkey application can randomly generate user events, such as clicks, swipes, and key press for automated testing. At the same time, it can record input events, allowing users to simulate specific scene behaviors. It helps us a lot in many products and find out a lot of memory leaks, no probability of crash. These are the enhancements we have done for NuttX in the past years. And finally, I'd like to share the landed products during past years. Then, a few visual work on the graphic and input subsystem. The VENA team has landed several products with display in the past 2 years, including smart bands, watches, smart panel, and some other products. They are all created with the newest graphic and input features, and benefits from these features. Let's see some video for these products. Finally, it comes to the future work. Firstly, we will still work on the enhancement of graphic and input driver framework for better user experience. Secondly, we would like to add a universal DMA 2D driver framework. Now, many vendors have implemented their own DMA 2D acceleration function. In the application, it needs to adapt to various DMA 2D modules. So we hope to add a universal DMA 2D framework to share the hardware difference and reduce application development workload. That's all. Thank you.
Thank you very much for the presentation. Do we have any questions for Xiaomi regarding the driver? Thank you very much for the presentation. Do we have any questions? It looks like we have no questions. We will take a lunch break, and after that, we will resume the sessions.
Hi, this is Neil from Xiaomi Vela team. Today I'm going to introduce you the memory debug tools and the GDB debug live demonstration. We already developed many debug tools. We will firstly have an overview of them, then focus on the memory tools. Finally, we will using the STM32 board to create a real crash and use the tools we learned to analyze it. And finally, we will use a GDB stub to actually debug the hardware. So why do we urgently need good debug tools? I will give you a real-world example. We have developed lots of wearable products. Most of them are based on Cortex-M microcontroller. They do not have MMU. For a large project, we normally need 3 major teams with more than 100 developers. So if anyone has developed a flaw in the code, it will lead to system crash immediately. So the importance for the debug tools is obvious because the code modules will affect each other. There is no isolation between them. Large team can increase the risk of flaws, so the stability is a real issue. With all the tools we have, is that really enough for the real project? The answer is never. We normally will combine several of the tools to debug a real issue. So here is an overview of what we have as of today. The first category is the static code analysis tools. There are free tools and non-free tools. These are really useful for a newly developed feature. The first thing we need to do is run a code check. And the tools are really useful because they will tell us exactly under what condition, for example, a memory leak will happen. The second category is the online debug tool. We connect to the hardware through GTAG, for example, using the G-Link. We can also using the GDB stub, so we can connect to device using UART or TCP/IP. We use the GDB plugins, so we can inspect the thread information and switch between them. G-Link, we also added the thread awareness support. The third category is the offline debug tools. When a system is crashed, all we have is the crash log. So the first thing we need to do is to get the backtrace to where the code causes the CPU to crash. With the mini dump, we can pass a little piece of the crash log to reconstruct the situation of the code stack. We can inspect the variables on the stack directly. With the code dump, additional to the stack information, we can also dump the heap memory. So for the for the real hard issues to debug, the code dump is a good tool. The fourth category is the memory tools. It includes stack overflow detection, stack canary, and the memory dump tool that will help us to debug memory leak issues. We also have address sanitizer tools and Fortify. So next section, we will focus on the memory debug tools. So let's firstly understand how stack overflow will occur. Here is an example of the heap memory layout. There is a stack memory allocated for task A, and then there are other memories. If we declare a real large variable on task A, it will directly overflow to other area, causes a stack overflow. If the task A has a really deep code stack, because the code stack is really large, it needs lots of stack space. It can also cause stack overflow, especially when the call is recursive. The fourth situation is that we use a function to write to the stack buffer, and under some circumstances, the input parameter is wrong, which will cause the buffer overflow to a higher address. So how we could determine how much stack is really needed by the task? We can enable stack coloration, which will write the whole stack with a magic number. There is a function will be used to check the deepest stack position. Hardware stack check is also available for some hardware. There is register called MSP limit and PSP limit. When the task switches, we program this register, so when we use SP as a base point to access memory, if the memory is outer range of the stack position, it will let us know. There is also a stack check using R10 register can be enabled by ARM version 7 or 8 stack check. Basically, it will insert a function call to every function. This function will be called to check if the function will use a stack space larger than we have. Stack buffer overflow is a common case we will face. Stack canary is a tool that will help us to debug overflows to the higher address. Here is a typical stack layout for a function call. We will firstly push some registers to the stack, for example, the return address. Then we will define the local variables. For this function, we will copy some data to the buffer address. If we copy more than 16 bytes to the buffer, it will overflow to the canary word. By checking the canary word if it is changed or not, we will know if the overflow has happened or not. Stack canary can be enabled by this macro. Once enabled, all the functions will be added this kind of check. It will slow down the performance a bit, but not that much. Fortify is another great tool provided by compiler. It helps us to do runtime checks against the buffer overflow. Here is an example of the memory copy function after using Fortify. Our real memory copy will be caught on the end, but before that, the parameter size, the parameter n, will be checked against the depth and the source object size. If we are going to copy more than the object size, it will assert directly. Currently, it covers most of the library functions. Fortify have different levels, and level 3 allows us to do heap check and stack check. Compared to Kson cannot do global variable check and stack check for now. Fortify also has a small impact on the firmware size and the performance, but it is limited to only check the library functions. Address sanitizer is also provided by compiler. Currently, it can only run on simulator, so it is useful for application development. The basic theory for address sanitizer is that the memory is marked as accessible or not on a shadow memory. So when memory access happened, the compiler will generate the code to check the shadow memory if it is allowed or not. Kernel address sanitizer, Kson, on the other hand, can run device directly. It can help us to detect out-of-bounds access to the heap memory or to the global variable. Currently, this feature is preparing for the PR. More importantly, it can help us to detect memory use after free, which is the downing pointer. Without Kson, this issue is really hard to debug. Kson is a great tool, but it also has some limitations because every memory access instruction is checked. So the firmware size and the performance will degrade a lot. We can overcome this limitation by optionally disable the read check or the write check. Based on the theory we just mentioned, considering this scenario that we have two tasks, if task A allocated some memory and freed it, task B is going will also need some memory, so it will unlock from the heap. It can happen that task A released the memory and task B require that memory directly. So Kson mark that memory is accessible because task B will use it. But after some time, task A wants to use that memory directly because it's a use after free. Kson cannot detect this case because the memory is already marked as usable. So to overcome this limitation, we included a feature called memory delete free. So when task A released the memory, we do not free the memory to the main heap directly. We insert the memory to a delete list, and when task B wants to unlock a new memory, it will unlock from the main heap. If the main heap doesn't have enough memory, then the delete list will be freed directly. So the system can run smoothly. With this feature added, when task B wants to use the memory it just released, Kson can detect this case. For the performance degradation and the firmware size increase, the hardware ASIN support is also added. In this section, we will talk about the memory dump function and the ECO memory leak and the memory corruption. So here is a typical memory structure. Beside from the essential manager info, we added a piece of statistic info, which includes information like where this memory is located, which is the backtrace to the function call, and what is the sequence number for this allocated memory. With this additional info, we can use command memory dump to dump all the system memories, and we can use free to check the heap memory usage. Memory backtrace can be enabled by this macro. When it's configured as -1, then it is disabled. The node overhead is only about the manager info, which is 8 bytes. When it is configured as 0, then it additionally includes PID of the owner of the node and the sequence number. When it is a positive number, it also includes backtrace to where the memory is allocated. With the help of memory dump, we can debug memory leak issues. So firstly, we need to determine if memory leak actually happened. We can do this by regularly call command free to see if the heap usage is increasing gradually. We can also enable scheduler dump leak, which will automatically dump the memory info that this task allocated but not freed. When the main memory is exhausted, we can enable dump on failure, which will automatically dump all the memory node info to the crash log. Besides from that, we can also use command memory dump to selectively dump memory info for the specified PID, for example, or for the user memory or the free memory. We can also specify the sequence number. Using tool pass memory dump, we can generate a report of the memory usage. For example, it includes the memory usage for every PID. It can also include the backtrace to the memory node. There is a trick to debug memory leak issue if we know for sure this scenario will generate memory leak. There are lots of threads running in the same time, so using memory dump directly will generate lots of memory node that is currently actually using, but not the leaked node. So here is an example that, for example, we have a UI that we enter this UI and leaves that UI, it will generate a leak memory. The trick is that before we enter this scenario, we firstly using memory dump command to check current sequence number. We remember this number and enter this scenario, and we do the normal operation, and finally we leave this scenario. And we check the sequence number again, we will see it is currently 1007. If we use memory dump command directly, all the red memory node will be dumped, so we cannot distinguish if the node is actually used or not. By specifying the PID to this scenario, so other threads will be excluded from the dump info, and specify the sequence number, so we will specify the 1000 to 1007. With this additional info, we dump the used memory. We will only have 1003. By checking the bytetrace to this node, we know where the memory is allocated, and then we debug why the logic to free this memory isn't executed. Besides from this trick, we can also use the leak sanitizer on the simulator. It's currently already supported. In the final section, let's talk about the JDB usage and get onto a real hardware. In this section, we will talk about minidump, call dump, and the JDB enhancement. Minidump is a useful tool that can be used when the system already crashed, but with useful logs. The log will normally look like this. It includes register value and the stack to the crashed thread. Using minidump server together with JDB tool, we can inspect the backtrace to where the system crashed. We can also switch to different frame and check the stack variable. Most of the crash will firstly use this tool. So with JDB stub, we can connect to device that doesn't have JTAG. For example, we can use the UART interface. Here I have an example that runs on ST32 discovery board. So previously we already showed the demo using minidump. I'm going to using the same board, but currently I'm going to use the TTY USB, which connects to UART3 of the ST32 board. Using this command through the UART, we can connect to the hardware. JDB plugin is a Python script that allows us to access to program status and memory. We can, for example, execute command info threads to check all the threads runs under NAS. We can also develop custom code to, for example, go through the list. We can make the print from JDB much prettier. Compared to minidump, which only allows us to access memory stored to the crash log, which normally is the stack memory. Call dump allows us to create a full snapshot of program's memory. It includes program's states such as memory content, processor registers, and stack trace. With the additional board memory range, it can also allow us to dump additional memory range to call dump. Call dump can be triggered automatically on when the board crashed, or manually by command call dump. It will use the lib.erf function to generate file content using ERF format. The data can be then streamed to the backend, such as syslog and the file stream. It can also be streamed to block device directly. The data can be optionally compressed by RZF to further decrease the file size. This is all the short introduction to the debug tools I have today. If you have more questions, feel free to file a GitHub issue. Thank you.
Thank you for the presentation. Do we have any questions from the room? Thank you for the presentation. Do we have any questions from the room?
I think now I would like to show the real life demo right now online.
Sorry, I just checked the share screen button, but it says that the screen share failed because of the permission. So could you help me out? Oh, currently it's not available.
I will display the agenda screen for a moment and we will return back shortly.
Hi, this is Neil from Xiaomi Villa team. Today I'm going to introduce you the memory Hi, this is much prettier. To use JDB stub, we firstly need to configure the baud rate for the device correctly, and then use JDB to connect it. After connected, we can execute info threads and other commands to inspect the system. It uses just like a G-Link. After system has crashed, JDB stub allows the system stays there so we can connect to it later. After connected, we can inspect all the variables. JDB plugin allows us to inspect task information. It also provides other tools. When system crashed, the backtrace will show the interrupt backtrace. By using NX setRex, we can restore the user task registers so we can see clearly which command and which task has caused this crash. Compared to minidump, which only allows us to access memory stored to the crash log, which normally is the stack memory, CalDump allows us to create a full snapshot of program's memory. It includes program's states such as memory content, processor registers, and stack trace. With the additional baud memory range, it can also allow us to dump additional memory range to CalDump. CalDump can be triggered automatically on when the baud crashed or manually by command CalDump. It will use the lib.elf function to generate file content using ELF format. The data can be then streamed to the backend, such as syslog and the file stream. It can also be streamed to block device directly. The data can be optionally compressed by RZF to further decrease the file size. To use CalDump, we can firstly add a baud memory range, so CalDump will also dump this range of memory. We create a crash and the system will output the CalDump data by syslog. We copy out the crash log and pass it to create a CalDump file. Then we can use JDB tool to analyze it. We can also use the info threads command and check frame by frame. We can also inspect variables in the heap. This is all the short introduction to the debug tools I have today. If you have more questions, feel free to file a GitHub issue. Thank you.
Yes, I'm ready. Thank you for the presentation, quite inspiring and useful tool. Do we have any questions from the room? It looks like there are no questions in the room.
Actually, I would have one question. So do you access the low-level debug peripherals with some interfacing like JTAG or SWD?
Yes, actually, we normally will use G-Link to use the JTAG interface, but for some system that doesn't have this interface, for example, the real product, we can also use the UART interface. To use that, we just use the feature we mentioned. It's called the GDB stub. So the answer is yes, we do actually use the G-Link and the JTAG interface to debug really hard issues.
Okay, so what can you access with UART? Because JTAG gives you access to the peripherals, the system bus, the CPU. So what are the options for the UART access?
So the UART works just like the G-Link. So G-Link just provides the hardware connection, and normally we will use the GDB server provided by G-Link and connect to the server to analyze the issues. With GDB stub, we just replace the JTAG interface with the UART interface. There are pieces of code running on the device in the interrupt handler directly, so we will when we access memories from the GDB client, the pieces or the code running on the device will perform the memory read and write for us. So it's just like how we use the G-Link hardware.
So you have the GDB server that serves over the UART, just like the J-Link serves over Ethernet or USB.
Yes, the GDB server code runs on the device in the interrupt handler.
Okay, very nice. Thank you. Congratulations.
Yeah. Okay, do we have more questions?
It looks like there are no more questions in the room or YouTube.
Okay, thank you.
Hello, everyone. My name is Takumi Ando. So today I will talk about how we use NuttX for small projects and small company. Hello, everyone. My name is Takumi Ando. So today I will talk about how we use NuttX for. Sorry. So today I will talk about how we use NuttX for small project and small company. So first, let me introduce myself. I'm Takumi Ando from Sapporo, Hokkaido today, and I'm an embedded programmer at Advari System. Advari System is our company name. So, and I'm invited by Koizumi-san. Yeah, Koizumi-san from Sony today. So I have experience mainly in Linux and other embedded system development. So this is my first time presenting in English, so please bear with me if my English is poor. Next is about our company. We are Advari System, embedded and IoT system developer based in Sapporo. We often use Linux for middle spec system and often use microcontroller for small and tiny systems. We develop various embedded and IoT solutions, including sensing system and camera system. So we are a very small company with a total of 16 employees, including 6 software engineers. However, we have a lot of projects, so despite our scale. Because of our small scale, we have some issues for development. One major issue is poor portability. We use various chips and boards, for example, STM32, Raspberry Pi Pico, ESP32, and Nordic chips. And before using NuttX, we use each specific DSP and SDK, like CubeID, Pico SDK, ESP SDK, blah, blah, blah. So we have no unified ecosystem for our project using microcontroller. We handle many projects at the same time, so we need to control our limited resources, and we have also some similar projects with different hardware because of some social reasons. But we have no unified ecosystems, so we need to develop similar but different code for each one. It wastes our time and human resources and increase development costs. Another major issue is poor resources. For example, if we want to use some devices with proprietary drivers, we need to implement them to our systems. But in many cases, such proprietary drivers only support for Windows, Linux, and POSIX systems, not for non-OS microcontrollers. Even if we use some RTOS, it is same as non-OS. Of course, we embedded programmers, so we can develop our own device driver for them. But we are a small company because of poor human resources. We have no time to do that. And in many cases, our projects are also short-term and no much budget. So we need to reduce development costs, including human and time resources. Next is, let me talk about meeting NuttX. We first used NuttX as a SDK for presence. We used presence for meter reading camera project. This is meter reading camera. Presence has LTE and camera extension boards, and they match to this project. Our meter reading camera captures values of analog and digital meters, and it sends photos via LTE to our cloud. In our cloud service, it does OCR from pictures, and values of meters are saved in database. This is effective for many meters because it is difficult to replace to smart meters, but our camera can recognize their values without replacing. Over 1,000 of these cameras are running around Japan today. In this project, we felt that NuttX is so good for us. First, NuttX has small footprint. It runs in so small microcontrollers, and its POSIX compatibility is so nice. We have experience for Linux, so NuttX is so easy to use and develop for us. In addition, a lot of supported devices, useful subsystems, they look so much for us. So we try to use NuttX in our other projects. Next, let me talk about our actual projects using NuttX and its effects. First case is an RC robot prototype. This project aims for controlling RC robots via 5G connection using PC and gamepad. This robot has RC receiver and basically controlled from a transmitter. Our customer of this project would like to control it via 5G connection for experimental usage. And it also needs to stream video from cameras. So we thought that using PWM from microcontroller instead of RC receiver and video streaming and 5G connection controlled by Jetson Nano Linux board. PC makes WebRTC session to the robot and control it with gamepad. Jetson Nano board and microcontroller are connected via UART. This is useful for WebRTC because WebRTC can make both video streaming connections and direct serial connection, virtual serial connection. PC receives commands from gamepad and sends command to the Jetson, and the Jetson throws them to microcontrollers, and the microcontrollers running NuttX changes PWM frequency. User can control the robot from PC in this way. In this case, serial commands implemented with Nutshell. This is so effective to reduce development cost. And it does and it doesn't depend on specific hardware, so we can switch to other hardware easily in the future. Also, NuttX has very small footprint, and it makes easy to scale hardware specs. These points were so effective for this prototyping project. Next case is Wi-Fi NFC reader project. This device has a Raspberry Pi Pico W and 15 LED switches and NFC reader. It was made for care facilities and hospitals. It is installed each room in facilities. Employees input what they did in each room by pressing switches, for example, cleaning, bathing, and changing clothes. Then they swipe off NFC card and the device sends status to the server. In this device, we use Sony's NFC reader, and it has own BSP for Linux systems. If we use non-OS or some RTOS without NuttX, it needs to implement its driver from scratch. It may take about a few weeks, I think. But in NuttX, it took only a few days to do that because of its POSIX compatibility. Make config file, make TTY, open it with BSP, and that's all. So we could reduce our time costs effective. These are projects using NuttX and its effects. Yeah, a few weeks to a few days. In conclusion, NuttX is so useful for small projects and small company like us. It's easy to use, highly portability, supports many hardware, has rich subsystems, and POSIX compatibility. So we decided to use NuttX as our standard platform for microcontroller projects. And we think that we should join and contribute for its development activity. Here we would like to thank all the developers. This is all for my presentation. Thank you for your attention. Thank you.
Thank you. An inspiring presentation showing how you got into the NuttX world and your commitment into joining the development. So I'm looking forward to see patches from your side. Do we have any questions from the room? Fuji-san, please.
Yeah, small questions. How many people, how many personal resources do you have in this NuttX project?
These cases is one only me.
So you can manage the whole NuttX project and also the other driver.
Idea currently.
Oh, super.
Any more questions? Yes, Alan?
How was your first contact with NuttX, and what do you suggest to community, for us as community, to improve NuttX? How to, what you feel more comfortable when you start using NuttX? What was your main difficulties, your main challenges?
It's a little difficult questions. I don't remember, but because
did you feel some issues, or it was easy because you was already Linux developer, so it was very easy because you have previous experience with it, or did you face some issues when stuff? I suppose Koizumi-san did many communication support for him to porting the NuttX country.
Oh, no,
No?
I just asked the company and, for example, some details like the LTE don't connect, disconnected too much. So how to do that? For example, such as support, production support we did, but no sales support for porting or something, making the application. So they did by themselves.
yeah, I just like NuttX, so yeah, that's it.
He would know very much.
Yeah.
Other questions? There are no other questions from the room. In that case, I have a question. Did you try writing some application for NuttX and then porting it on Linux, or the other way around?
NuttX to other OS?
No, NuttX to Linux or Linux to NuttX.
Yeah. I used to port Linux application to NuttX and NuttX to Linux.
Did you encounter any difficulties in porting the applications?
I used to try with Zephyr. It's so difficult, but NuttX is so easy.
What a surprise.
Thank you very much.
Is that right answer?
There is no right and wrong. We as a community are happy to have another community member joining. And we also are interested on what was your journey, like my colleagues asked, like I asked, because we all had the same experiences. 2 years ago, last year, I had a presentation on how to port applications from one side to the other. Masayuki-san also had the same experience, and he also shared his experience. And this kind of interoperability and reusability is the key, or at least for us is the key. And we were curious, I was curious, and Fuguchi-san was curious, what was your experience? So it's important to know what others think. You know, you have your shiny gem and you think that is the best, but the others may not consider the same. So that's the reason why we are asking, and we are glad to hear that you were not having too much difficulties.
Thank you.
Thank you for the presentation, and thank you for taking your time and spending the effort to have, for the first time, a presentation in English.
Thank you too.
Hello world of Apache NuttX RTS International Workshop 2024. I will tell you today about sport shooting lane control computer made with NuttX, created together with my friends from Cover Sport Shooting Club located in Poland. My name is Tomek Cedro, also known as Cederom. I'm the independent ICT researcher, open source by heart. FreeBSD is my favorite operating system, and NuttX is my favorite real-time operating system. So I'm also kind of crazy inventor, creating tools, libraries, designs, devices, rapid prototyping, reverse engineering, and stuff. In my free time, I really like skydiving. The sport is really good, and allows me to take rest from this computer world. It keeps my mind, fresh and focused, as well as body. The healthy spirit lives in a healthy body. Especially the extreme sports enable you to, react in a constructive way, to focus on the solutions, in a problematic situation. So that also is kind of useful skill in solving real life problems. So having this kind of, friends around is very inspiring. And we are sharing, together our skills. We are helping each other. So I'm usually the computer and electronics guy. So this project is kind of result of a, friendship and open mind to experimentation. So what's the problem? One of the locations has 10 lanes that are already around 20 years old. The company that created the system is not on the market anymore, and servicing, is really hard. Not to mention the design, the maintenance, where you don't have the replacement parts available is really hard. Increased, rate of failures in recent times, revealed this possibility that the whole system probably needs a replacement soon. So we decided, to create something on our own. Of course, we can buy a very complex and expensive, system, but we just need something that will work, and provide one-to-one compatibility replacement. Because we are creating this system on our own, then we are able to add some new functionalities that were missing in the old system. We can design the modular, system that will be easily replaceable, upgradable, and open for all kinds of experimentation. So I wanted, and as most with my projects, we are using only open source components, the software libraries, tools, and the NuttX is also open source with lots of different, drivers, functionalities. So that's the perfect candidate. So this is my first design and first device, first project made with NuttX. Another problem are the components. So recent, supply chains problems revealed that it's not really good to use highly sophisticated and hard to get components. So we are using only commercial off-the-shelf, really easily replaceable, inexpensive, easy to find components. And with this kind of approach, with friends open for experimentation, we created this system. So how the lane works? There is a someone that wants to practice. There is a paper target attached to the car that is then operated with a electrical motor. The electrical motor is controlled by the lane computer, and the lane computer gets the directions from the pilot controlled by the user. In our case, we have the 3-phase 4 volts installation. The motor is also 3-phase motor with brake, or sometimes without brake, and the positioning is achieved by using quadrature encoder. So we can see how it looks in reality. The box is the control computer. This is the old system for comparison. We can see the cables, going inside. The cables, I can tell you, are screwed inside. So with that many cables, it's really hard to service, this kind of part. Imagine replacement of this kind of box. There is a 3-phase motor, using the rubber belts for the wheel. That, by the use of metal line, provides the traction for the car that we can see on the right side picture. And the target is attached, below the car. There is a grip. So positioning of the system can use quadrature encoder. Other systems use Hall sensors. So you can see on the left side picture the O-ring that is attached to the axis, and then this O-ring has 10 magnets that provide impulses to the Hall sensor. From the electrical standpoint, it works almost equally the same as the quadrature encoder. So our new device can use both Hall sensors and quadrature encoders. The other methods for distancing is may use laser sensing or time of flight, but remember the car moves really fast, so the information provided here needs to be really rapid, to provide the good feedback loop, as this is the real-time application. And we can see the pilot. Pilot is quite simple. There are two buttons. One uses the target desired range, and the other button, the green one, is used to move the target back and forth. And the LEDs above are indicating current position and desired position. So the block diagram of the new design we can see right now was designed with a modular approach in mind. And also everything had to be connected with using cables and sockets and plugs, because this is the experimental device, so we want easy maintenance, easy servicing later on, but at the experimental stage something might get broken, something might need quick replacement, so we need to be able to easily reconfigure the whole system. So the power supply is provided over the socket. There is a power switch, there is a motor control block protected by fuse. Computer, the electronic device called here the motherboard, is protected by emergency stop that shuts down the computer, that shuts down the motor control. Computer is also protected with easy accessible and easy to replace fuse outside the box. One also important part here are the power indicators. So the previous design didn't show really if the power was connected or not. The new design has two power indicators that will at first glance reveal if the external power is connected. Either the power switch, the main power switch, is turned on or off, so we will know if it's safe to operate inside the device to open it, and the other lamp shows the activity on the computer. So each of the components, the functional block has this its own connector, and the motherboard consists of power supply. Each of the functional block has its own, power domain based on DC-DC converter. So in case of failure, other blocks will be operational. Inputs, outputs are protected, with optical isolation. Then also we have the positioning control block, the CPU board based on NuttX RTOS. There is a CAN controller UI with LED RGB stripes, or the SPI LCD screen, and the audio speaker. So the CPU board is also in a form of a dedicated separate printed circuit board, because if, for example, one MCU doesn't fit the requirements, then we can easily or gets burned, for example, we can easily replace that board with some other board. We can easily replace the board with different firmware. For example, this application really requires rapid servicing, so the disturbance in operations in here with this design can take around 1 minute, right, to replace something. So this is the first prototype that is already operating. We can see it resembles the block diagram pretty close. We can see the panel with the connectors, the high power relays to control the motor, the fuses, the power supply, and so on. And I will tell you right now how did that happen step by step. So the first challenge was to have the 3 power supply at home, which is not really common because we usually have one phase only with 230 volts. We need 400 volts AC 3-phase connection, so I had to buy a power inverter. I'll also played with some plugs, different plugs and sockets for the power delivery. I decided to use this kind of plug that will use female connector, and it will be closed by design. That provided security, and in case the whole device need to be detached, no wires, high power wires will hang in the air. There will be just a plug, that we can detach, attach, and it will be fairly safe to use. I also was verifying the control of the phases delivered to the motor, because the motor direction depends on how you attach the phases L1, L2 and L3. That provides the clockwise movement, and if you connect L2, L1, L3, that provides the counterclockwise movement. So that was the first challenge and experiment to see if we can operate this kind of motor at home. Okay, so it works. You can see 6 connections. Normally you will use the star or delta configuration, by connecting those connectors to the power supply. In our case, it was, I will tell you later on how the motor operates. So then I had to create the lane simulation. Of course without the car, of course without the wire, but just something that will resemble the target configuration. So there is a metal plate, there is a motor mounted on additional metal plate that can regulate the rubber stripe stretch, and there we have the traction wheel that use 2 slots. One is for the rubber belt from the motor, and other slot is used to mount the metal line that it's attached to the car, and by rotating the wheel we achieve the movement of the car. So another problem was the quadrature encoder. These are not really available anymore, and their mechanical design is kind of different than the modern ones use. So there was this kind of metal adapter on the slot, as you can see. I had a problem with obtaining these components, and I didn't really wanted to use hard to get components, so I researched the modern encoders, and I had to create some kind of adapter for that. The movement axis is attached to the encoder with use of clutch. You can see on the picture that sometimes this clutch was broken in the old systems, and this requires also 2 holes, one on the mounting part and the other in the adapter, because the clutch had to be screwed to the axis and to the sensor. So initial test was made with 2 metal plates, and some screws. That was really hard to maintain, and also it didn't provide any protection against the dust, because it's a closed place, but it's very dusty. So we need to invent something that will also provide some cover against the dust. And after some months, I couldn't find, the inexpensive CNC service, or someone that will design this. For me, my friend, hinted me that we can use, the plastic. So I created the prototype on the 3D printer. It turned out to be fine. And then my friend created the CNC with, kind of more resistant plastic. So this is the upgrade of the old system on the left hand side, and the right hand side we can see already the new system. The electronics was designed in KiCad, of course. The printed circuit board initially was created with rapid prototyping precision CNC machine. It's the 2 layers 2 sides printed circuit board, and when everything was ready, I ordered the boards from the factory, and then it was kind of fun, to create 10 boards like that. You know, we can see the semi-smart pick-and-place machine, neural-based, you know, self-sufficient. I'm really proud of that machine, but maybe one day I will be able to get, you know, the real one, pick and place that will allow me to create, you know, like 10 boards, 10 devices per day, or maybe 100 devices per day. So I recorded the whole process. I wanted to show you some better time lapse, but you know, like hundreds of hours, you know, compressed into 1 minute, that wouldn't make sense. So I will upload it to the YouTube. If you like, you can watch it. I'm not a YouTuber, beware. So then I had to create a casing. The metal casing wasn't really much more expensive than the plastic one, and it turned out it had a metal plate that could, you know, mount all of the components. This also gave us the possibility to replace everything, you know, inside once the device was mounted on site. One good thing here is the rivet nut. That's very neat, you know, solution. I recommend it to you. These rivet nuts are really great way to mount anything everywhere. Then I had to create holes, you know, in the casing. The manual version, as you can see, wasn't that good as expected, and also I had to create, you know, the cables with all of the connectors from the motherboard, from the components to the casing. It turned out, for example, that the plastic, you know, so-called industrial grade plugs were breaking very easily, so it was quite a lot of work with the cables. So then I decided to switch to metal sockets and metal connectors. They are far better and also not that much expensive. We can see that the power supply socket and the main power switch is located on another board, so they could be also replaced just in case. And the manual drilling, you know, of the holes in the casing, I replaced that with the metal panel that was beautifully crafted with the CNC machine, and then it's just, you know, attached on the screws. Also on the rivet nuts. One thing I would improve right now is not to create every single cable from the panel to the target. I would, in the next version of the hardware, I will just create a cable, you know, the ribbon cable, ribbon tape that will provide, you know, the single connection from the motherboard to the printed circuit board that will be located below, you know, here the panel, and of course the high power supply, the motor control socket, will require dedicated cabling, but this will save really lots of time and work. So right now we can see the upgrade. We are not using single, you know, cables that are screwed inside to the motherboard. They are unlabeled, you know, it's like 50 or several tens of those cables, so the servicing was quite painful. Right now we have the metal casing. Everything is using cables, connectors and sockets, so everything can be easily replaced, you know, or modified. The metal plugs, you know, as you can see, are doing well. So the last part to do is quite trivial. It's the pilot. There are pilots like this available already on the market. I just had to create the holes for the LEDs. That was quite challenging, so I invented, you know, to create a PCB that will provide the mask for drilling, and that enabled, you know, the precise drilling for the LED sockets. Also the LED board later on was screwed, you know, for easy replacement with these nice nuts that could be heated up, you know, melted into the casing, and that was quite elegant solution. Other components of the pilot were created with 3D printer, and you can see the final version of the pilot, you know, on the picture below. So this is the old pilot on the left side picture, and the new pilot on the right hand picture. They are quite the same, provide the same user experience, nothing fancy. So this is the upgraded system. You can see the old system on the left side photo. and the new system on the right side photo. You can see that the power is connected with the power plug. There is a power switch that can, you know, power cycle just in case the whole system. There is a fuse socket easily available at the bottom, and the two lamps that indicate, you know, whether the external power is provided and whether the computer is operational. So you can see the test without the moving car and without the metal line yet. This is installed on the old components, so that proves the one-to-one compatibility. Also notice how fast is the motor and how fast, you know, the wheel turns. And this is the movie showing the car already attached and the system, you know, operational in the real world scenario. So we are using the motor that is dual speed motor. It basically consists two coils inside the single case. By connecting three phases to one set of three connectors, we have the low speed. It's around, depending on the construction, 900 RPMs, and connecting three phases to the other three connectors, we have the high speed. So it's around 2700 RPMs, depending on the construction. So the LEDs are showing, you know, the current state of the lane, where is the target, where is the car. Fast blink indicates fast movement, slow blink indicates slow movement. You can see that computer calculates and displays the current position of the car that wasn't present in the old solution. Okay, the NuttX part. So I did use the out of tree build, you know, so to keep the firmware code separate, the application code separate from the NuttX, and then this allows the easy NuttX upgrades. There are some automation scripts for configuration, build, flashing, so anyone else can easily, you know, make some modifications or build the firmware. I used the custom board definition based on the example. I used the ESP32, so thank you, Alan, for the example I could use. One thing I had to improve was the quadrature encoder. The default hardware provides 16-bit resolution, so I had to extend this resolution to, you know, higher number just to get, you know, the direct position number, not to process this information inside of the application. So there are several custom applications, you know, that are launched when the device starts. When we provide some input from the UART, then we will trigger the command line interface with some additional utilities for configuration, calibration, testing, logging and stuff. And then, you know, if nothing like this is triggered, then we will start the default application. So I would like to also add the non-volatile storage, you know, for the calibration configuration. It is not required right now, but also I'd like to add Wi-Fi and Bluetooth for remote control, maybe synchronous work, internet platform that could, you know, read out the state, maybe possible failures and servicing requests. CAN bus can provide the additional pilot implementation, maybe some additional sensors or interconnection with external systems. I'd like to play with MCU boot, of course, and some fancy display driver and LED RGB. So the problems and plans for future, these are mostly caused by the electromagnetic interference. You know, this three-phase high power motor is really big source of interference. High power relays are located inside the metal casing, so this is also a source of the interference. And maybe installation, you know, a structure, it's metal, needs also good grounding. So everything, you know, vibrates, so this is the mechanical challenge. Over time the components were replaced, so we need to invent our own designed mechanical components that will be also inexpensive, you know, to manufacture and multiply. it happens several times that the ESP32 hang on running motor. That requires the power cycle of the device. Although the watchdog was enabled, I'm not sure what's the cause, probably DMI. That needs some more investigation. In worst case, maybe I will try to use STM32 instead. NuttX allows easy porting, you know, of the firmware to different hardware. So STM32 is known to work in automotive industry, so maybe that's the case of MCU. I'm not sure yet. It's work in progress. So improved isolation, filtering, shielding, and also I'd like to try to use the power converter to control the motor, because so far we are using simple, you know, one-to-one backward compatible design that is using power relays, but this does not provide, you know, the full control of the motor. Also, the two-speed motor is quite expensive, you know, and the replacement of several of these motors is quite expensive. So with power inverter, we could get, you know, the smooth control of the speed of the motor, and also we could implement really cheap motor that should be sufficient in this case. So thank you very much for your time. Thank you for your attention, and big thank you for Gregor and Nat for creating NuttX. That's my new love. I tried several RTOS before, and I really like the, you know, this rock solid, old school Unix approach on, you know, microcontroller level CPUs. Kudos, respect, you know, everything, all the best. Thank you for your attention.
Thank you, Thomas, for the presentation, an inspiring presentation. Let's see if there are questions in the room for Thomas. Yes, please. Thank you, Thomas, for the presentation, an inspiring presentation. Let's see if there are
strategies that you found in NuttX for this application? Because we could argue that we could do without a real-time operating system at all, for example. Okay? And so just before we had a presentation for small apps and so on, and the portability, thanks to NuttX, several advantages were great from that perspective. But from the perspective of your use case, share the advantages of NuttX. Thank you.
So the question was, what is the biggest advantage of NuttX? I guess that was the question. Well, the previous presentation showed the NuttX is kind of unified ecosystem that can be used in various, you know, environments. Other people here shows many different applications. So from my standpoint, it's a really nice environment to work with, kind of BSD Unix that I really like, but on the microcontroller level. So of course it could be created on 8-bit MCU, written in assembly. But for example, then I couldn't have the internet connectivity, the Bluetooth implementation would be harder. In case of failure or decision to extend the design into a more powerful MCU, I would have to create everything from scratch. Right now, I can easily port the design, the application, the firmware to totally different platform. I just need to see if the drivers are there. Probably they will be there, and maybe just need some adjustment or extension, like I did with the QEncoder. I don't know. There are lots of advantages.
Thank you for the explanation, Thomas. Do we have other questions? If there are no other questions, I would have a question. For this application that you realized, are you considering switching from the high voltage motors to a stepper motor assembly?
Well, so far it was one-to-one replacement, kind of retrofitting. Some of my friends I consulted with bigger experience in mechanical design, they showed me some stepper motors or some dedicated motors. It turns out they are more expensive, require dedicated power supply and also the control block. So I guess in this application, fairly simple three-phase motor, is enough. It's powerful, and maybe with control over the power inverter, it could provide smooth velocity control. That would be better characteristics than just switching with the relays. And what it turned out, that the biggest power spikes are generated over the power line and surrounding when the motor starts, but also when the motor changes speed. So for example, if the car is moving fast and then we are detaching the power supply and then attaching power supply to get the low speed mode, then the kind of strong power spike occurs. So maybe if we had this, power inverter, the power spikes would be smaller. I don't know. Some people, told me not to use power inverter because they are killing the engines and they are generating the EMI. But in the current situation where I'm already facing, horrible EMI, I will try. Why not?
I see. Thank you very much for the explanation, and good luck with the implementation.
Thank you, Ali. Thank you, guys.
Alan, do we have questions online?
No.
There are no questions online. I propose that we continue with the next presentation in this case.
Hi everyone, thank you for joining me today. My name is Mateusz Szafoni. In this presentation we will explore the current progress of x86-64 port in Apache NuttX. For convenience, in this presentation I will use the term x64 to refer to x86-64 architecture. At the beginning, a few words about me. I am NuttX contributor since 2016. I work with NuttX for fun, and that's where most of my contributions to this project come from. But also I work as an independent contractor trying to use NuttX wherever possible. The presented work is the result of my collaboration with Xiaomi. So from my side, thanks to the Xiaomi team for the code review, suggestions and testing. Some of the changes mentioned during this presentation are already in the NuttX upstream repository. The rest will be added in the coming weeks. So let's start with ACPI support in NuttX. ACPI is a component present in almost all modern computers. It is standardized interface used to perform power management, device discovery, and configuration tasks. For now, we are only interested in hardware components discovery feature. This means that what we need is to extract some data from memory that are provided by BIOS in a format of ACPI tables. That's why a simple custom ACPI parser was implemented. Alternative for this custom solution was ACPI CI project, which is an open source OS independent ACPI implementation. So why didn't I choose this solution? There are two reasons. First, we only need a small piece of its functionality which can be easily implemented. Second, it doesn't follow the NuttX coding standard. To parse ACPI tables, first we have to locate special RSDP signature in the memory. Currently, it's supported to search for this signature in a legacy BIOS area or get it directly from the multibot tag. At the moment, ACPI parser is located in the x86-64 architecture directory, but in the future we probably should move it to a location available for other architectures. Here we can see an example dump of ACPI tables for QEMU. If necessary, the tool can be improved to display more details from ACPI tables, but for now the current functionality is sufficient. HPET is 64-bit up counter timer. It's a hardware timer located on the chipset, so access to it is over memory area, unlike the TSC timer, which is an on-die timer on modern x64 processors, which can be accessed by CPU registers. In NuttX, HPET is implemented as one-shot timer and work in one-shot mode with legacy interrupt support enabled. HPET comparator triggers interrupt on equal condition, not greater or equal, which is a huge design flaw which can lead to interrupt miss in one-shot mode. To prevent this, we must explicitly specify the minimum supported interval for a given platform in the configuration so that the comparator update always triggers the interrupt. For example, for QEMU, this value is quite huge, around 1000 microseconds, but run directly on the Intel processor that I have around is around 10 microseconds. It's worth mentioning that HPET in some processors is unstable, and in Linux kernel it's blacklisted for some Intel CPUs. Now a few words about math acceleration in x64 processors. I will deal with two types of hardware acceleration in x64 here. The first is legacy x87 instruction set, which is not as essential after making SSE2 available by default in x64 according to specification, but still can be useful for some high precision calculations. And the second one are SIMD vector instructions. SIMD instructions are disabled by default until the operating system explicitly enables them. Support for SSE instructions above SSE2 was trivial, and it came down to adding some compiler flags. AVX support required more work, and a new method of saving FPU context had to be supported, which will be discussed in the next slide. Support for a given instruction set must be enabled from the NuttX configuration level, and NuttX configuration must match the features supported by the processor. There is no dynamic selection of supported CPU features. So if we enable a specific instruction set in the configuration, but it's not supported by the hardware, NuttX crash at the early boot step. Unfortunately, at this boot stage, serial port is not available, so we don't get any valuable error message. CPU state must be saved during context switching. That means also vector registers must be saved and restored. AVX instructions require new xsave and xrestore instructions, support for saving and restoring CPU state. Xsave has different requirements than the previously supported by NuttX fxsave instructions. It needs 64-byte alignment buffer, but fxsave needs 16-byte alignment. Xsave buffer size depends on the system configuration and set of enabled features, while the buffer for fxsave has a fixed size. Some additional control registers must be configured for Xsave, and each Xsave call behavior is controlled by EDX and EAX registers that must be written on each Xsave call. For now, only standard Xsave instructions are supported, so there is no support for optimized version of these instructions. When it comes to math library support for x64, we have two reasonable options to choose from. The first one is OpenLibM, which uses x87 legacy instructions for many math functions. And the second one is NuLibMath library, which depends on compiler optimization, and compilers prefer to use vector instructions. NuttX Math library is also supported, but it has limited functionality and is not x64 optimized, so its use in real-world application is limited. I also experimented with the host toolchain libm. Unfortunately, it doesn't work. The host x64 math library is tightly coupled to the host libc, which results in a lot of compiler errors. Optimized string functions were ported from Bionic project, which is an implementation of the standard C library developed for Android, which is BSD license. Optimized functions used vector instructions and can be enabled when a given x64 vector extension is enabled in the configuration. Unfortunately, the FPU test from NuttX OS test doesn't work for x64 when high optimization level enabled. The problematic part of the code is present on the left screenshot. In short, how this part of code works. First, we perform some floating point operations and locally store FPU context. Then force the program to do some context switches. And finally, compare the current FPU context with the previously saved one. If everything went okay, the FPU context should be the same and the test succeeds. The reason of this failure is the for loop presented on the right screenshot, which is executed when sleep is called. The compiler uses a loop vectorization technique for optimization, which uses vector instructions, the same vector instructions used for floating point calculations. This results in modified FPU context, which breaks FPU tests. On this slide, we can see CoreMark result for Linux and NuttX. We can see that Linux performs better and is better about 6%, so there is still room for optimization somewhere, but I haven't explored the reason for this difference yet. And changing optimization flag to 03 doesn't make too much improvement for the NuttX result. Now let's talk about SMP. In x86 terminology, the bootstrap processor or BSP is the first processor that is booted. All other processors are called application processor or AP. This BSP in SMP initializes each core's private data and wakes up the AP cores with inter-processor interrupt. To send API to the processor, we need to know its local APIC identifier. This is where we need the previously mentioned ACPI. The BSP reads the local APIC ID value for a given core from the ACPI table and creates a map connecting the local APCI ID with the logical CPU ID. To optimize SMP performance, we use the special purpose GS register to access frequently used data such as current regs and CPU ID. This is a popular OS dev technique for x64. In x64, FS and GS registers are used for a limited form of segmentation. We use special instruction to save the base address for FS and GS, and we can later refer to the data stored at this address in a simplified way. The images show access to current regs stored in private CPU data and the generated assembler codes that use the GS segment. The FS register is not yet used and is reserved for 3 local storage implementation. Here we can see result of PS command run directly on Intel i7 processor with 12 cores enabled. The system passes the SMP test present in NuttX apps correctly, but the output of this program is too long to fit on the screen. Here we can see CoreMark result with 12 cores enabled. Linux also performed better in this test, scoring about 10% better than NuttX. Now let's move on the important element of every x64 machine, which is PCI. Probably every x64 application requires some degree of support for PCI devices. Support for MSI and MSI-X has been implemented, as it is currently the primary interrupt method for PCI cards. Legacy PCI interrupts are often not even supported by new hardware. But this old interruption method is still used, for example, by some of the QEMU drivers. MSI support requires some improvement to x64 interrupt logic, such as support for all possible interrupt vectors and dynamic vector allocation. To communicate with real hardware without a legacy UART port, it was necessary to implement support for PCI serial card. Currently, cards based on AX99100 and QEMU simulated PCI serial device are supported. In addition, support for Intel i219 and Intel i225 network cards was added. Their implementation is based on NuttX NetDev upper half logic. For now, no advanced card features are supported. Side note from me, Intel network cards are terrible mess. Some have undocumented hardware bugs, some cards from the same family but a different series may not work with the same driver. Sometimes it's really hard to find the reason for the problem, and often you won't find the solution in the Intel documentations. Kernel mode is still under development. Initial RAM disk is supported with multi-bot header, so we can easily include RAM disk with group. ELF support was ported from x64 simulator, and per task address environment seems to be working properly. What is missing is syscalls and support for ring 3 privilege mode. Now, important note about security. Currently, there is no protection against speculative execution vulnerabilities such as Spectre or Meltdown. While some issues have been fixed in newer Intel processors, many of these vulnerabilities still require fixes at the operating system level. Implementing these OS level fixes often comes at the expense of performance, which is particularly problematic for critical real-time applications. This may or may not be a problem, it all depends on the application, so risk analysis must be done for a given use. A few words about what can be done in the future. First, we can add support for more PCI devices, including NVM, CAN bus cards, USB and more. We can add support for graphical interface and keyboard support, so we can run NuttX directly on the hardware without need of legacy serial port or PCI serial card. Another thing is support for AMD processors, and of course we need more testing, performance optimization, more code review, and code quality improvements. Now some ideas for when we might need x64 with NuttX. When our application needs high computing power or requires a large amount of resources like RAM, flash, or a large number of cores. When we need to run simultaneously real-time operating system and general purpose operating system. In that case, we can use one of the available real-time hypervisors. In that scenario, we can separate critical real-time functionality from non-critical work. This approach can help us with safety certification when required for specific parts of our product. Another case is when our real-time application needs to communicate with PCI Express devices like high-performance network interfaces, digital acquisition cards, or any other devices that can be implemented as PCI card. Maybe NuttX will become a good alternative to RT Linux in the future. Some more specific application examples are kind of industrial equipment like multi-axis motion controllers for robots or CNC machines, when in real time we have to control motors to achieve complex movements. Real-time Ethernet controllers, for example based on EtherCAT protocol. Advanced flight controllers for avionics or drones, so we can combine Linux tools like computer vision with real-time tasks like sensor integration, flight control, or others. Some laboratory equipment like data acquisition systems where we can use Linux as user interface and real-time OS for precise timing and data collection. Or even more exotic applications like high-frequency trading where low latency is crucial to make money. That's all from me. Thank you for your attention. If you are interested in the topic, I encourage you to test and help improve the x64 port in NuttX, as it may bring many interesting applications in the future. Thanks.
Thank you for the presentation. We are now, unfortunately, Mateus is not with us. I had a few questions, but we will have to thank him, even though he's not here, and probably continue with the next session.
I'd like to add, I was considering the first question I received to the previous presentation. So, of course, the design of the operating system is important, but what convinced me most is the community. Community of, passionates, and that is so inspiring that this convinced me to the NuttX. And then, when I got into internals, the internals revealed, to be beautifully designed. So I think it's the internals of the operating system, but also the community.
Thank you, Thomas. From my side, there would be a small concern on doing this kind of activity because most Intel CPUs will not work correctly without microcode that has to be loaded. And you don't really know what that microcode does. And also, most Intel CPUs require performance scaling to be able to even achieve performance benefits, because otherwise your turbo modes will be low. And then you need thermal management so that you don't damage the CPU. So there are many things that have to be implemented before we can see NuttX running on x86-64 Intel CPUs.
Maybe it could become a microcode itself.
Yes, but we don't have documentation. The next presentation is from Yashita-san, which is here with us in the room. Please display the schedule while we will arrange the next presenter. Background. We use very old kernel, NuttX 7.26, on our evaluation board. Still now, we think naturally to update it. But the guy who ported it to our evaluation board has already left our project. So I decided to update it by myself, although I didn't know the NuttX kernel well. The goal of porting: confirm to boot nutshell with NuttX 12.4 on our evaluation board and contribute the code. What I did: at first, reading the NuttX document. Second, analyzing the NuttX boot sequence. Third, implementing the SOC and board. Fourth, contributing the code. I'll explain them. Reading the NuttX document. I read a part of NuttX document as below listed. It was a bit hard work for me, actually, because of my poor English. Anyway, I got a lot of hints by reading these documents, but not enough to know the details of how to port NuttX, although I think it is normal for OSS kernel. So I decided to analyze NuttX kernel code about the boot sequence to get enough knowledge. Analyzing the NuttX boot sequence. I think to port NuttX properly, we have to understand the boot sequence and related kernel configurations. This sequence diagram is the one of my analysis result. At the analysis, I assumed CXD56 and non-SMP and flat build. The beginning of boot sequence is __ start. __ start we call NX start. NX start will initialize the kernel and call NSH main. NSH main will execute nutshell. NX start is NuttX standard function, but the behavior depends on some kernel configurations. For example, the calling NSH main is also configured. I think almost today's listeners have well known this sequence and related kernel configurations, but a beginner like me will not know. And I found following kernel configurations by analyzing the boot sequence. I think it is good to consider them, although almost all of them might be set as default. And implementing the SOC and board. Based on the analysis of boot sequence, I think the build system will teach the list implementation for SOC and board directly, and these implementations are almost done by copy and paste from the other SOC and board directory if there is the source code for the target hardware IP in upstream. If there was not the source code in upstream, the porter should implement by himself. In my case, I referred the implementation CXD56 because our SOC has same CPU and serial as CXD56. I implemented the SOC and board with following steps. Step 1, add and register the SOC and board directory. Second, configuring. Third, compiling. The compiling will teach what source files are needed by SOC and board directory to pass the compiling. Fourth, linking. The linking will teach what symbols are needed by SOC and board directory to pass the linking. Implementing. I did implement the symbols, which are needed by linking. 6. Verifying. I got a problem to boot nutshell about this. See the pull request about vector. After got successfully the boot,
I checked the timeline implementation and did OS test. I love OS test. I really appreciate the developer of OS test because I think the path of OS test is one of proof proper porting. Although I don't know the details of OS test, but anyway I got the proof. This made me to reduce the time to verify. And contributing the code, I invoked the 3 items, this pull request, and already merged. I appreciate the reviewer for these pull requests. And last slide, feelings. I think the guy who wants to port NuttX is expected to understand NuttX kernel code and related kernel configurations, but getting enough knowledge is needed to read the kernel code deeply. To reduce the time for NuttX beginner who wants to port, I will try to make the guide based on my porting journey and contribute it. That's all. Thank you for your listening.
It is really nice to see a second person stating how easy it is to port NuttX to a new board and to share the porting experience that he had to also share a bit of the experience. And thank you, Miyashita-san, for your intention of sharing the porting guide.
Yeah, I think it will be very useful.
It will be useful for many developers and maybe many companies that are afraid of trying because they don't know how to know it is the entry barrier.
Yeah, I think we have a documentation on guide how to port, but it was very old and by Greg himself, and he has a very high level, very video. But for end users, it's better to have some more abstract ideas how to do it because it makes it simple to someone have the because for example he already know everything about the system. So you don't know all the traps that you fall. So you know that now when you do the yeah.
Also, from when that guide has been done until now, we have many more platforms, architectures actually, that have been added, and then if your board isn't, it's just to port.
Exactly.
Like Miyashita-san's case.
Yeah.
If you are supposed to use a new architecture and you start implementing the architecture from scratch, then Greg's guide is great.
Exactly. I think there are many levels of the because you can just port a new board for some microcontroller that already exists that's similar to other board. That's the easiest part. Or you want to add a new microcontroller like the CXD32, right? The other Sony chip, and that's another level of difficulty. And there's this other case that
Which is the hardest.
The hardest that the manual that Greg created is very good because he go all the details. But this is the most difficult part because you are create something really from the scratch. Yeah.
Thank you very much. Do we have other questions from the audience? Please.
Do you have some plans to release CXD32?
Good question.
Plans to release the CXD32 hardware to the market?
We want to continue the contribution about CXD32, but our project now prioritizes release. So contribution is suspended now, unfortunately.
The question is not about the contribution, it's about the hardware.
Hardware.
Can we get the hardware if we are
developers?
developers?
I'm talking about
hardware. Sorry.
Something like board or
engineering samples.
Of course, I want to sell our evaluation board in market, but our business strategy does not have such plan. Sorry.
So maybe at a later time there will be a version that we can use.
Yeah.
Next generation.
Let's hope for it.
I think it's a rare case for not released board and implementation. So I think I want to use new board.
Hopefully we will have it.
Not released board, but implementation is exists.
Only SOC. Only SOC directory. Board directory is located out of 3.
Not for board.
Yes. And so we have to continue to check the upstream by ourselves.
There is some question from Thomas in the chat. How long it took to start the porting? How the porting went? So
actually, almost activity was reading document and analyzation. Implementing the time of implementing was not so long, only 2 or 3 weeks.
2 or 3 weeks, good. And here asking about what was the CPU, but I think we already said it.
I think that we need a clarification, and I'm quite curious. So you say 2 to 3 weeks. Was that implementation done all by yourself, or you had a team that worked for 3 weeks?
All by myself.
So it's 3 weeks manpower.
Or yeah,
one member.
Yeah.
Nice.
Fuki-san, you had a question.
Yeah. Just a small question. So can you give the developers who want to start NuttX or to contribute to the NuttX community? So from your journey, do you have any, if you can give us some advice, it is very useful.
If I can, I want to.
宮下さん。
なんか今から開発したい人とかにアドバイスありませんか？
アドバイス。I think anyway reading code. At first, reading the code. Yes. So I want to make a guideline.
How easy was to contribute to the NuttX project? Because I saw that you have a few contributions listed. How easy was it to contribute to the code?
Maybe for beginner, the hurdle is a bit high. In my case, Ishikawa-san follow me. Ari follow me. Koizumi-san follow me. That is my advantage. You make me to the hard low. How do I say about this? I was just follower for you.
We contributed to the NuttX community, but my question was, how hard do you feel that was to push the patches and then get community review, basically?
I think basically, the guy who wanted to involve plurality needed the skills about embedded software. But the guy who has such skills, not so difficult, I think.
Nice. Thank you very much. Do we have other questions?
It's not question, it's kind of the comment. Yeah, about the guideline. I think of course, the guideline is, I think it's not only the kind of the document. For example, if we could, if we provide kind of the script to generate the template or the skeleton things, and for example, the execute the script with specific CPU architecture, then generate the kind of the template. That is much more easier to
convenient.
Yeah.
I think that is another solution. But I think that solution needs the maintenance cost.
Yeah. Of course,
And also, we miss on the developers that will understand the platform, because everything will be generated. They will take it as granted, and then when you end up with a bug, you don't really know where to get it from.
It's a two sides of the same coin. It's easy because you can automate the process, but it's like the artificial intelligence today. It can do everything for you, but you never know what it's doing at the end of the day.
Of course,
But I think the script will be.
So yeah, both things is important. The guideline, like your journey, and script to make it quick. Yeah.
Okay. Let's move to next.
Yes, just give me a second.
Okay. Thank you. Very good.
Thank you very much.
Greetings, NuttX developers around the globe. I am Rushabh Gala, excited to be here with you for the workshop. Under Google Summer of Code 2024, I am porting NuttX apps to Rust. Currently, I am in my third year of studying computer science and engineering at Mumbai University in India. Today, our focus shifts to the realm of IoT security challenges and the tools that aid in their development. The rapid expansion of IoT brings it with a significant security concern. According to White House, ensuring memory safety is the main concern for the creation of secure software. Next, we will discuss what is Rust. Rust is our ally in this endeavor. Rust is a swift, modern language that prioritizes the safety of our code without sacrificing speed. Then we will discuss about Cargo, which is a project managing tool. Driving the charge is aux64 single board computer, a versatile platform for IoT applications utilizing Rust and NuttX. Supporting our journey is the QEMU emulator, our trusted companion in testing, faithfully recreating hardware virtual environment for the NuttX application. Memory safety stands as a cornerstone of our challenges. Rust ownership system boldly eradicates null pointers and buffer overflows, ensuring steadfastness of our IoT ventures. Rust indigenous methodologies including zero-cost abstraction and streamlined runtime, empower our NuttX devices to maximize the potential with minimum resource consumption. In the realm of security, Rust stands as our strong guardian. Its robust type system and vigilant borrow checker fortify our communication, fortifying our protocols against vulnerabilities. In the essence, the integration of Rust into NuttX blankets our project in a cocoon of security, addressing memory consent, concurrency, resource optimization, communications, and platform fortification. Now we dwell into a significant subject highlighted in the recent report from the Office of National Cyber Director (ONCD). This topic holds significance for NuttX application. The message conveyed by the White House report is unmistakable. We must address vulnerabilities in our software promptly. It strongly recommends the adoption of memory-safe languages. In the face of ever-evolving cyber threats, it becomes imperative that we elevate our cybersecurity efforts to the implementation of enhanced metrics. We can identify and eliminate vulnerabilities before they escalate into critical issues. Let's unravel the mystery of Rust. Shall we? Rust is a cutting edge Swift solution tailor made for system operation. Now let's us discuss the main features of Rust app. Memory safety. We bid farewell to memory bugs with stringent regulation of Rust. Rust ensures our memory remains steadfast and secure, a crucial aspect for NuttX application. Next, borrow checking. Rust diligently oversees our resources, ensuring seamless operations within the RAM of NuttX. Enhanced abstraction. Rust boasts a range of sophisticated techniques that optimizes the performance of our applications. Robust type system. Rust's formidable type system serves as a bastion of stability and security for our application. It preemptively identifies and rectifies issues, offering invaluable peace of mind for NuttX endeavor. Next, about the community interest for Rust. Mr. Gregory Nutt, the pioneering creator of NuttX, alongside a crowd of esteemed colleagues, had discussion regarding the integration of Rust into NuttX. Now let us discuss about difference in C and Rust code for a basic LED key application. In Rust, we print the strings as a pointer to an unsigned integer, whereas in C we directly print it as strings. And next difference about the dot into function. Rust conversion method for enum variance to integers, while in C we can directly use the enums or the constants. In Rust, we do not have any long type. We can directly use 500 into 1000, while in C, we need to use 500 into 1000 L. Next, about the return type. In Rust, we directly return 0 by explicitly stating it only. In C, we need to write it as return 0. Now let us discuss about cargo. Cargo manages all the components necessary for our projects to operate seamlessly. And what Crates.io is the Rust official package manager. Now, why the reluctance toward cargo? The NuttX developers thrive on maintaining a firm grasp over their system components. Cargo's automatic dependency management may not align seamlessly with the strict requirements of embedded systems. Furthermore, abstaining from downloads helps for security and stability of our systems, mitigating unforeseen disruption. Should the external sources encounter any issues in future, it could disrupt our code building process, leading to unwelcome compilation in our development journey. In essence, while Cargo proves to be a convenient tool, NuttX developer prioritize control, meticulous dependency management, and mitigating external risks above all else. Let us now address the holders we encounter by opting out of using Cargo. First and foremost, dependency management poses a significant challenge. We have to manually procure and assemble each dependency. Ensuring proper linkage is essential for the functionality of NuttX application. Next, we confront the build system dilemma. Without cargo, we must establish and execute our own process independently. Moreover, the Rust ecosystem flourishes harmoniously with cargo. By bypassing it, we risk falsifying access to many invaluable tools and libraries of Rust. Among others, now we have challenges about cross compilation, testing, documentation, project initialization, and versioning. These challenges underscore the significance of meticulously considering our dependency and build procedures in Rust. I am thrilled to share the exciting news that Pine64 has generously sponsored me the remarkable OX64 single board computer for my Google Summer of Code 2024 project. Today we are embarked on an exhilarating exploration of OX64 boards and its companions. Now let us delve into the essence of OX64. At its, at its core, the OX64 is a RISC V based single board computer boasting the formidable Buffalo Lab BL808 RISC V SoC with C906 64-bit CPU core, supplemented by additional E907 or E902 32-bit CPU cores. But wait, there's more. We have another 64 MB of embedded PSRAM memory on OX64. This ample resources allows us to meticulously, seamlessly execute Rust application, and behold, the diagram on the right side depicts the OX64 pinout diagram. It serves as a reference point for those curious about the board's design. Next, discuss about QEMU. It is an indispensable emulator in the hands of developers. QEMU serves as a free wizard akin to a free virtual brain for computers, enabling the execution of diverse operating systems seamlessly. It's like having a multitude of computers encapsulated within a single entity. Furthermore, QEMU possesses the remarkable ability to facilitate cross-platform compatibility, allowing tracked programs tailored for one computing architecture to operate seamlessly on another. This versatility proves invaluable for experimentation across diverse systems. QEMU boasts the capability to emulate a myriad of computer architecture ranging from x86 architecture and ARM to PowerPC and RISC-V among others. In essence, QEMU stands as an indispensable tool enabling developers to explore, test, and innovate across a spectrum of computing environments with unparalleled ease and efficiency. Now, let us recap what we have discussed so far. First, we focus on memory safety and security challenges in IoT. The recommendation by OECD report on memory safety and cyber laws. Next, why we discuss why we use Rust and how we use it, and a simple example of an LED blinking app. Next, we discuss about Rust cargo and why don't we use cargo in NuttX development. We also had a quick look at OX64 board, a powerhouse for embedded computing, opening doors for innovation in IoT and beyond. Next, we had a quick glance at QEMU emulator. Before we wrap up, I want to extend a huge thank you for joining us today and the NuttX organization for giving me this opportunity. Your participation and engagement have truly made this discussion worthwhile. Now let's open the floor for any questions you may have. Please feel free to ask. Thank you.
Sorry, before we start the Q&A, that was the presentation by my student, Rushabh. Okay, I'm his mentor for Google Summer of Code. So Rushabh will be here to answer the questions for his presentation. And I will step in to answer the difficult questions. Thank you.
Thank you for the presentation. Thank you, Luke, for lending a hand. Do we have questions from the room?
Sorry, before we start the Q&A, that was the presentation by my
Do we have questions from the room for Rusha?
Perhaps a clarification. I'm not sure to understand whether they recommend or not to use cargo.
Can you please speak a bit louder, because otherwise the microphone will not pick it.
Perhaps a clarification. I was not sure whether you recommend to use or not to use cargo with NuttX.
Did you understand the question?
Get the question clearly. Can you please repeat the question?
We have difficulties hearing you. The question was if you recommend or you don't recommend using cargo with NuttX.
Personally, I won't recommend using cargo in NuttX for now, as we are still in the development phase of integrating Rust properly into NuttX. We have set up the infrastructure and the basics for Rust, but we still need to go ahead without cargo. Thank you.
Thank you for the clarification. Do we have other
Okay,
questions?
maybe I can step in and clarify, since I think Rusha is having some audio problems. So we are sticking with the status quo for now. As of today, Rust builds on NuttX without cargo. Because of the concerns that we saw earlier on the slides, that we are able to import libraries from other places, and embed it into our NuttX build, which might be a bit scary. So we're sticking with the current situation, trying to use Rust without cargo, which means we're calling the Rust C compiler directly. And also, Rusha has mentioned, there are some limitations. That means we cannot use external crates, external Rust libraries. If we ever create a Rust wrapper for NuttX, it will be a problem. Which means right now we need to integrate the wrapper individually into each Rust project, which is kind of messy. Also, there's a kind of build process problem we have today. We might switch to a more powerful build process, like say CMake, to solve this problem. But that's actually something that Rusha and myself will need to settle during the GSOC project. It's going to be a summer-long project. We'll try to address these issues, and we'll make a final recommendation whether we should use cargo or not for NuttX.
Thank you.
Thank you for the clarification, Lou, and thank you for the presentation, Rusha. Any other questions from the room? It looks like we do not have other presentations from the room, so please, Tomek, play the next presentation.
Hello, everybody. I am Lup from sunny Singapore. Over the past 7 months, we did many fun, cool things with Apache NuttX RTOS on AUX64 BL808 RISC-V single board computer. I shall explain everything in this presentation. If you would like to download the presentation slides, please head over to this link, lutyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation transcript, articles, and source code are available at that link. Yet we had endless hours of fun over the past 7 months with NuttX on AUX64 SBC. In this presentation, we begin with the porting of NuttX to AUX64. Interesting things we saw in memory management, interrupt controller, and NuttX apps for AUX64. Then we created an emulator for AUX64 that will boot NuttX, which is super helpful for automated daily testing, also for automated log analysis. Finally, we go wild with NuttX on AUX64. Stretch it to the limit. Do all kinds of things in NIM, JavaScript, drag and drop apps, tiny C compiler. Some folks watching this might be receiving AUX64 boards. To install NuttX on your AUX64 SBC, please follow the instructions here. If this link is too long to type, just browse to hexter.io/Labyuan and you will find the OX64 article there. Remember, this is the letter L, not the digit 1. What is this BL808? BL808 SoC is a curiously complex creature with 3 asymmetric RISC-V cores. One 64-bit core based on T-head C906. This is the multimedia core with MIPI, CSI, and DSI, and neural processing unit. NuttX runs here. One 32-bit core based on T-head E907. That's the wireless peripheral core with Wi-Fi, Bluetooth LE, Zigbee, audio, USB, and Ethernet. NuttX doesn't run here yet. But we don't touch this. The 32-bit low power core based on T-head E902. Today we shall talk about the OX64 single board computer by Pine64, which is the development board for the BL808C SoC. BL808C supports MIPI CSI cameras, but not MIPI DSI displays. We could potentially connect a MIPI camera module to OX64 and turn it into a security camera. Here is a demo of NuttX on OX64 single board computer. OX64 boots NuttX on a micro SD card thanks to the U-Boot bootloader. OX64 has plenty of RAM, 64 megabytes. That is why we can run a JavaScript interpreter on OX64. Here is our JavaScript that blinks the LED by calling the NuttX POSIX API. When we run it, yep, it blinks the LED. Later in the presentation, we shall explain how we ported the Quick.js JavaScript engine to NuttX. Porting NuttX to OX64 was surprisingly straightforward. We took NuttX for Star64 RISC-V SBC, made a few tweaks, and it runs on OX64 SBC. Here is a helpful tip for porting NuttX to a new RISC-V device. Inside the NuttX boot code, we can insert RISC-V assembly like this. It prints something to the UART serial port, so we know if NuttX is built in on this device. And this works without fixing the memory map or kernel loading address because all this RISC-V assembly code is independent of memory address. This printing will always work regardless of the RISC-V device, assuming we have the correct UART base address. We did the same for porting NuttX to TinyEmu emulator. Check out the presentation here. Next comes the UART driver for NuttX, which is harder to port to new devices, especially for SoCs with special UART controllers like BL808. Here is a quick hack to make the UART driver work. We took NuttX from Star64 G8710, which still runs on the 16550 UART driver. We patched the UART driver so that it writes to the BL808 UART output register. With this quick hack, our NuttX UART driver will print boot logs and crash dumps to BL808 UART output, buying us some time to port the entire BL808 UART driver. One last thing we do to boot NuttX on OX64 SBC, we update the system memory map and the NuttX build configuration. The boot address 5020 hex comes from U-Boot bootloader. We are looking at the memory management unit of the OX64 SBC, visualized as an animation. What exactly is this memory management unit? Memory management unit, or MMU, is the hardware inside our single board computer that does two things. Memory protection. MMU prevents applications and kernel from meddling with things in system memory that they're not supposed to. Virtual memory. MMU allows applications to access chunks of imaginary memory and exotic addresses like 8000 hex. But in reality, the system RAM recycled from boring old addresses like 5060 hex. Inside AUX64 SBC is the SV39 Memory Management Unit. We call it SV39 because SV is the name of the official RISC-V extension for supervisor mode virtual memory. 39 because it supports 39 bits for virtual addresses. If you can't remember SV39, just remember 3 levels of page addresses, each level adding 9 address bits. So we have a level 1 page table, which points to level 2 page table, and maybe level 3 page tables. Here we have the bits to indicate if the page table entry is valid, whether it points to read-write or read-only memory. If the G bit is set, it means this chunk of memory is mapped across all memory spaces. Then we have the physical page number, pointing to the actual chunk of memory. This is how we map the interrupt controller for AUX64 with a level 2 page table. Do we use level 3 page tables in NuttX? Yep. This is the level 3 page table for kernel code. That's why the execute bit is enabled. Here we see level 1, which points to level 2, which points to level 3, which points to the executable kernel code. This looks tedious and confusing, but we had to trace through the page tables to troubleshoot some memory management problems in AUX64 SBC. We talked about NuttX kernel. What about NuttX apps? Here is the level 3 page table for a NuttX app. It points to the virtual memory for the executable code of a NuttX app. The U bit is enabled, which means this chunk of memory is accessible in RISC-V user mode. To learn more about the RISC-V page tables, check out my article here. Okay, thanks, but why are we learning all this? Well, we had to troubleshoot some really strange memory issues like this. Get Prime app runs okay on NuttX. After that, we run the Hello app, but it crashes with a page fault, which is totally weird because 8020 is a valid address for NuttX apps. Why is this happening? First, we need to understand that inside our RISC-V machine, there is an SATP register for supervisor address translation and protection. The SATP register points to the currently effective page tables for kernel and apps, and the SATP register gets swapped when we switch between kernel and apps. Is there a problem with the SATP register swapping, causing our Hello app to crash? We found the answer by inspecting the Linux kernel source code for AUX64. Remember that AUX64 runs on a BL808 SoC, which uses the THC906 CPU. But THC906 uses special RISC-V instructions to flush the memory cache. Thus, we call these magical RISC-V instructions whenever we swap memory spaces between apps. And it works. No more crashing. That was pretty scary, hitting strange new RISC-V instructions never seen before in NuttX. There's another thing unusual about the THC906 CPU. You know how when we press a key and it triggers an interrupt for your input? This is how we normally handle the interrupts for your input. We program this with the PLIC, Platform Level Interrupt Controller, which is a standard interrupt controller for RISC-V. But AUX64 and THC906 CPU works a little differently, when we write to the PLIC interrupt controller. The writes get mashed up, leaking over to adjacent interrupt registers. The interrupt registers won't tell us which interrupt was fired, which gets super frustrating. So I walk to the beach, ponder my life choices, and suddenly I realize, what if we are not reading and writing our I/O memory correctly? Now, this problem doesn't happen before we enable memory management. It only happens after we enable memory management. Something to do with the page tables and the memory management unit. Again, we check the Linux kernel source code, how they configure the page tables for aux64, and we discover a special bit for strong ordering. We must enable the strong order bit inside the page table entry so that reads and writes will be executed in the correct sequence. Again, this is a special feature specific to T8C906 CPU. Everything works great in NuttX for aux64 right after we enable the strong ordering bit. For NuttX on 32-bit devices, most of us use NuttX flat mode. This means that NuttX apps are statically linked into the NuttX kernel. For NuttX on 64-bit devices at aux64 SBC, things get more exciting and complicated. NuttX apps are actually compiled into ELF files like this Hello World app. And NuttX apps on aux64 are relocatable. See this call to the puts function? The address of the function will be filled in by the NuttX ELF loader when it loads our NuttX app for execution. This is good to explore in detail as we figure out how to bundle NuttX apps into the aux64 image. Also, we will revisit this when we run TinyC compiler to compile NuttX apps. Back to our puts function. Our app will print something to the console, but NuttX apps can't write directly to the serial device, right? Nope, that is because NuttX apps run in RISC-V user mode. NuttX app can't access the serial device, which is controlled by NuttX kernel. That's why our puts function should eventually trigger a system call to the NuttX kernel, jumping from RISC-V user mode to supervisor mode. This is what we see when we enable system logging for NuttX system calls. How exactly does a NuttX app make a system call to print to the output console? Will NuttX apps require some special code to make system calls? Nope, not at all. The system call is totally transparent to our app. Our NuttX app will call a normal function named write that pretends to be the actual write function in NuttX kernel. It works by forwarding the write function call and passing the parameters to a RISC-V system call like the syscall3 function here. What's inside the syscall3 function? Syscall3 makes a system call to NuttX kernel with 3 parameters by calling the special RISC-V instruction, eCall. Later, we'll generate this system call with TinyC compiler, and we'll hit some very interesting problems. That is why we are going so deep into NuttX apps and system calls. We said that NuttX apps are individual ELF files. Where do they live? Well, they are bundled into a ROM FS file system. We call it the initial RAM disk or initial RD to follow the Linux terminology for bootable file systems. We started by loading NuttX kernel and initial RAM disk separately into RAM, but it became a hassle for U-boot bootloader. Thus, we just appended the initial RAM disk to the end of the NuttX kernel. U-boot bootloader will load everything into RAM, NuttX kernel, and NuttX apps. NuttX kernel will then search our RAM for the ROM FS file system because the ROM FS file system has a magic number, and copy it into the designated memory region for mounting. That's how NuttX kernel accesses the NuttX apps. We trace through and figure out how NuttX kernel boots on aux64 SBC. Check out the entire process in this article here. And this is how NuttX kernel starts a NuttX app on aux64 SBC. Remember, the steps are more complicated because you're running in NuttX kernel mode instead of NuttX flat mode. Check out the details here. How were we able to accomplish so much over 7 months with NIM, JavaScript, TinyC compiler, all running on aux64? Wouldn't it take us a lot of time to port and test the new NuttX drivers and apps? Well, we became super productive because we created a software emulator for aux64 SBC, and it boots NuttX. We took TinyEmu emulator and create an emulator for aux64 SBC. aux64 emulator runs at the command line and inside our web browser, thanks to WebAssembly. Today, we run it daily for automated testing, which is triggered by GitHub Actions. aux64 emulator makes it really quick to test and experiment with new NuttX drivers and apps. We have another presentation on the TinyEmu emulator for aux64 SBC. Please check out the presentation at this link. We are looking at the emulator for aux64 SBC running inside a web browser, though it runs okay at the command line too. We see that NuttX boots perfectly on our aux64 emulator. This is NuttX compiled for aux64 without any changes. This works because we customized the TinyEmu emulator to emulate the aux64 memory map, UART controller, and GPIO controller. For details, check out our presentation on TinyEmu emulator. It's already 2024. NuttX is running on single-board computers with plenty of RAM, like aux64 with 64 MB of RAM. Can we make good use of the extra RAM, like for creating memory-safe apps for NuttX? NIM is a newish programming language that has garbage collection and reference counting, so it works better when there's extra RAM. This is how we blink an LED in NIM. We call NuttX to open the LED device, call iocto to flip the LED on or off, call uSleep to wait a while. And here is the loop that repeats the entire process. NIM looks similar to Python, so NIM is good for folks who are familiar with Python. How will NIM know about open, close, iocto, uSleep? This is how we import the NuttX functions from C into NIM. Notice that NIM imports C functions directly from C header files. This works because NIM programs compile into C code, which gets compiled and linked into NuttX with the exact same GCC compiler. This means we get seamless integration between NIM and NuttX. NuttX is officially supported by NIM, thanks to the NIM community. And today, NIM is also supported by NuttX. So go ahead and check it out here. We have plenty of RAM on NuttX now. Guess what also needs plenty of RAM? JavaScript. QuakeJS is probably the tiniest JavaScript engine, and it supports POSIX functions. Lots of fun possibilities with NuttX. We might use QuakeJS for interactive, iterative experiments on NuttX. Yep, QuakeJS runs okay on NuttX for aux64, and we can blink the LED in only 4 lines of JavaScript. We open the LED device, then call iocto to flip the LED on and off. Here is our JavaScript that blinks the LED by calling the NuttX POSIX API. When we run it, yep, it blinks the LED. Later in the presentation, we shall explain how we ported the QuakeJS JavaScript engine to NuttX. The really awesome thing about QuakeJS is that it supports POSIX functions. So it is a perfect fit for NuttX. But IOCTL is missing from QuickJS, probably because it's too platform specific. Thus, we added IOCTL to QuickJS with a few lines of C code. Do we just compile QuickJS for NuttX and expect it to work? Nope. Remember that NuttX was created for tiny microcontrollers. Some of the NuttX defaults are really tiny. Feels a bit like micromanagement, and here's why. We compiled QuickJS for NuttX with nearly zero changes, but when we run it, it crashes with this crash dump. And this is a strangely loopy crash dump. It loops on and on and on forever. Took us a while to figure out, but NuttX ran out of stack space. We increased the NuttX app stack space from 8 kilobytes to 64 kilobytes, and QuickJS runs okay. No more loopy crash dump. Then we noticed that the QuickJS ELF executable was huge. The ELF executable was 22 megabytes. By default, NuttX apps are partially linked and relocatable. Most of the 22 megabytes is filled with relocatable symbols. Hence, we converted the NuttX app from partially linked to fully linked, which reduced our app size from 22 megs to 4 meg, and it loads a lot quicker on aux64, since the NuttX ELF loader doesn't need to fix up the relocatable symbols. How small exactly is QuickJS? Will it run on smaller microcontrollers? Because a JavaScript engine with POSIX sounds really helpful for NuttX. We generated the linker map for QuickJS and we ran this visualization tool, linker map viz. We discovered that QuickJS with all the toppings needs 550 kilobytes of code and data. What about heap usage for QuickJS? We turned on heap tracing in NuttX, which is actually called memory management under the logging option. We captured the heap logs, imported into a Google spreadsheet, and monitored the heap allocation over time. Barebones QuickJS uses 280 kilobytes of heap space, since JavaScript depends heavily on dynamic runtime memory for managing JavaScript objects. That's 780 kilobytes for code, data, and heap. QuickJS with all the fixings, it uses 370 kilobytes of heap space. That's nearly 1 megabyte for code, data, and heap. So yeah, if we have a supersized NuttX device like aux64 SBC, QuickJS will run on NuttX. Remember our demo earlier with QuickJS running on aux64 emulator, blinking a simulated LED? How did we simulate the LED? We tweaked our aux64 emulator based on TinyEmu to watch out for all writes to the GPL register of the BL808 SoC. Our emulator sends a notification to the web browser JavaScript so that it renders the simulated LED in HTML, flipping it on and off. aux64 emulator becomes really helpful when we start emulating onboard peripherals like GPIO and LEDs. Now that we have JavaScript running on NuttX, what are the fun ways of creating JavaScript apps for NuttX? Maybe something drag and drop like Scratch? That is why we are hopping on to Blockly, the popular drag and drop toolkit for creating JavaScript apps. As a NuttX app developer, all we need to do is to drag and drop the blocks to create this visual program, and Blockly will emit this JavaScript code. We are looking at a demo of drag and drop apps for NuttX, powered by the Blockly Visual Programming Toolkit for JavaScript. Here we are dragging and dropping an app that blinks the LED by calling the NuttX POSIX API. At the left is the JavaScript code that is auto-generated for our visual program. We can run this on the OGG64 emulator, our web browser JavaScript will automatically send NSH commands to transmit our visual program into the emulator. When it runs, OGG64 emulator will blink the simulated LED. The same works on a real OGG64 SBC. Here we use the Web Serial API, which is supported by modern web browsers. Our web browser JavaScript transmits NSH commands and our visual program to OGG64 over the USB serial connection. QuickJS runs our program and blinks a real LED on OGG64. We have seen the drag and drop app builder for NuttX. Here are the internals. Our app builder generates a JavaScript program that will run on our OGG64 emulator in a web browser with WebAssembly. The same JavaScript program also runs on a real OGG64 single board computer. We use the Web Serial API that is available in most browsers to send NSH commands to OGG64 over the USB serial console. To blink an LED, we need to call POSIX functions in NuttX. That is why we added these POSIX blocks to block B: open, close, iocto, and sleep. For each POSIX block, we created the code generators that will emit the JavaScript code for the POSIX block: open, close, iocto, and sleep. Remember, we are running all this on QuickJS JavaScript engine, which works great with these POSIX functions. How do we magically run the generated JavaScript on OGG64 SBC? In modern web browsers, we have the Web Serial API that will control any device that is accessible over the serial port. We use the Web Serial API to send NSH shell commands and QuickJS commands from the web browser to our OGG64 SBC. Our commands are transferred line by line, but remember that serial I/O is unreliable and might drop characters, so the data transfer is kind of slow right now. We might switch to Z modem. To control OGG64 SBC from a web browser, we click the Connect button, which will show a list of serial devices. We click Connect, and our JavaScript takes over, sending NSH and QuickJS commands to OGG64 SBC. Okay, JavaScript runs fine in a web browser, and JavaScript works okay with NuttX emulator and real NuttX devices. What about plain old C? Can we let NuttX learners write NuttX apps in C, compile them inside a web browser, and run it in a NuttX emulator or a real NuttX device? Let us try it with the simplest C compiler, Tiny C Compiler or TCC, and run it inside a web browser with WebAssembly. At the left is a bare-bones NuttX app that will print something. We compile our NuttX app with the Tiny C Compiler, which produces a RISC-V ELF executable. Our web browser JavaScript copies the ELF executable to OGG64 emulator, injected via the ROM-FS file system. And it works. OGG64 emulator runs the compiled program, printing something to the NuttX console. We compiled Tiny C Compiler from C to WebAssembly thanks to Z Compiler, which calls CLang to convert C to WebAssembly. But there is a problem with WebAssembly. Tiny C Compiler was created as a command line app. It calls POSIX functions to open source files and to read them. And WebAssembly running in a web browser ain't no command line. We counted 72 POSIX functions needed by TCC compiler but missing from WebAssembly. Thus, we fill in the missing functions ourselves. Effectively, we're emulating POSIX in WebAssembly by writing our own Zig functions. Now we have TinyC compiler running inside our web browser, and it compiles our NuttX app from C into a RISC-V ELF. Our JavaScript copies the RISC-V ELF into AUX64 emulator, and it runs okay. TinyC compiler didn't seem to generate the correct RISC-V code for NuttX system calls. We tweaked the RISC-V code and made it work with system calls. Here comes another problem with TinyC compiler. We need C header files like stdio.h, but WebAssembly doesn't support file systems. We added a read-only file system to our WebAssembly, the ROMFS file system, and we host the C header files inside the ROMFS file system. We modified the code in our Zig wrapper for TCC, emulating the POSIX file access functions by calling the ROMFS file system. And how did we get the ROMFS file system running inside WebAssembly and Zig? Well, NuttX has a ROMFS driver in C, so we ported the ROMFS driver from C into Zig. Our Zig wrapper emulates POSIX file access for the TinyC compiler by calling the ROMFS driver. Yep, we actually took a chunk of code from a real-time operating system and ran it inside a web browser. Zig compiler will compile the NuttX driver for ROMFS with a few minor code changes. Then we can call the driver from Zig WebAssembly. In Zig, this is how we mount our ROMFS file system, by calling the NuttX driver. The driver integrates really well with Zig. The file system checks from NuttX are still in place. If the ROMFS file system contains garbage, our ROMFS driver will fail the mount operation because it searches for a magic number at the top of the file system. Also in Zig, this is how we open and read a ROMFS file. The NuttX driver for ROMFS works great with Zig inside a web browser. Next time we're thinking of using NuttX drivers outside of NuttX, just go ahead and try it. It might surprise you. While porting NuttX to AUX64 SBC, we wrote plenty of detailed notes. Check out the articles here. More articles here. Yep, we are looking at 7 months of detailed documentation. Everything we know about AUX64 SBC. And these too. Remember, you can download these slides from this link, lutyuan.github.io/NuttX. That's the letter L, not the digit 1. We have 2 more presentations on AUX64 SBC, about the TinyEmu emulator for AUX64 SBC, and the analysis of real-time logs from AUX64. Please check out the presentations at this link. Today we had so much fun with NuttX and AUX64 SBC. Porting NuttX to AUX64 was surprisingly quick, maybe because NuttX runs better on RISC-V SBCs. We created an AUX64 emulator that is super helpful for daily automated testing and regression testing. We saw today that NuttX is no longer a boring textual RTOS. NuttX really shines when we experiment with new things like NIM, JavaScript, drag and drop apps, even TinyC compiler in a web browser. Let us do many more wow things with NuttX. Thank you. Hello, hi, I'm back. If anybody has any questions.
Hello.
Hello.
Hey. Actually, I have some questions. You told it was about 5 months to get all these things done, but how much time did you get, for example, to get the TinyMu ported, to get the TinyC compiler ported uh, to run in the NuttX in the browser? So I think you are very good on that and very fast, and you are inspiration for me and for many other people. Many here follow your uh, amazing work. And could you please tell a little bit more about that and explain how you can do so much things so fast and you are creating incredible documentation about NuttX itself?
Yeah, sure. So, okay, so how did I do so much so fast? Actually, 7 months. So I guess I was fortunate. So I actually took a lot of work from Mr. Fabrice Bellard, Tiny Emu emulator, QuickJS compiler, so QuickJS JavaScript engine, and a TinyC compiler are all his work. And his work is actually quite excellent. And the beauty of his work is that the code is quite small. Tiny Emu was the first thing I ported over for customized for Quick Aux64. That was actually a very simple emulator, and it does one thing very well, which is to emulate RISC-V systems. So actually, the code is quite minimal. It's quite easy for me to tweak it to work for Aux64. Now, after that, everything runs quickly because once you have the emulator running up, then it's a lot easier. Everything I do on QuickJS JavaScript engine, just test it on emulator. Everything that I do for TinyC compiler, again, test it on emulator. So it took me about, say, maybe about 2 or 3 weeks to port TinyEmu to emulate an Aux64. Then after that, it took about 3 weeks again for QuickJS and another 3 weeks for the TinyC compiler. So I think it was a lot quicker than I expected because we are using emulator. And also, I was very fortunate to be using the TinyEmu emulator, which is excellent RISC-V emulator, very small compared to QEMU, and I managed to customize it for Aux64 in a very short period of time.
Oh, okay. Understood the idea. And about the tiny tiny C, you implemented it mostly, as you said, most of that functions, that POSIX function was emulated in Nin, right? Um, do you think it is fast or easy to get the tiny C now running inside NuttX in a real board instead of running in the web browser? For example, in that um, o, uh, OX64 boards or like that, BL 604 or 804. Yeah.
Yeah, right. So the question is, yes, I took QuickJS to run it in the web browser in WebAssembly, which is actually a lot more difficult because there's no POSIX functions in there. So it's very hard to take a command line app and run it in a web browser. And yes, it will be a lot simpler to run it under NuttX because NuttX is command line. It has POSIX support. However, I have some issues with the code generator. So I'm not sure if TinyC compiler is ready for all platforms. The platform I tested is for RISC-V, and I had issues. I tried to reuse some of the system call code from NuttX, tried to emit the RISC-V machine code for our NuttX system call. It just didn't work. So there's something wrong with the compilation. Okay. I'm thinking that we might have an issue with the different kinds of platforms. RISC-V has got issues. We're not sure it is well supported. But ARM, I'm not so sure. Actually, I'm not so sure if TinyC compiler supports ARM that well. I believe it was the support for X64 might be a bit better. Yeah. Sorry, my webcam is blanked out. Okay, but yeah, so it is platform specific. So there are some platforms that work better.
Okay, thank you. I think we are have some issues with your internet. It was
yeah. Sorry.
Now I think now it's yeah. I think now it's going is returning, but I'm not sure.
The camera feed is blurry.
Yeah. I'll let.
Yeah. Sorry about that. I'll just go without with my camera. Yeah. If you have any other questions.
Questions here in the audience. Anyone has more questions to look?
Yes. Thank you for the presentation, Luke. One question would be if there is a performance difference between the emulated code and the real hardware. Did you see any obvious differences in code speed?
Yeah. Okay. So the question is whether there's any performance difference between our Ox64 emulator and the actual Ox64 board. Yeah, definitely yes. Surprisingly, the emulator was a lot faster than the board. Um, if you notice, the form factor for Ox64 is actually a very tiny board. Even though it's 64-bit, it's actually like a lower end SBC. It's not really a full-blown SBC. So some things are a bit downscale. The RAM access speed, I believe, and the CPU speed is kind of slow. So in fact, the emulator runs a lot faster on a computer, even within the web browser. And that actually was one of the issues I have with emulators. How do you make sure that the timing is accurate? I haven't solved the issue. Like today, when I run OS tests on emulator, it's actually a lot faster than running OS tests on a real Ox64 device. So maybe someday we'll figure out how to emulate timing correctly. But as of right now, the timing is off, for sure.
Thank you very much.
Thank you. We have a question here from Thomas about the Java. Why did you do you use JavaScript instead, for example, Python? And he also asked if the QuickJS or QJS is faster or is smaller than MicroPython, for example.
Okay. Okay. Thank you, Tomac. So, QuickJS is just purely random. I just saw that it's a JavaScript engine, and it's actually very small. And the thing I like about it is that it's POSIX compatible. So it has POSIX functions in QuickJS that will map actually to the POSIX backend. So when you compile QuickJS, you can actually run POSIX programs quite well. Only thing I added was the IOCTL. So IOCTL IOCTL isn't supported by QuickJS. It took me just a few lines of code to support it in QuickJS. So that is why I'm able to do the blinking of LED, because blinking of LED in NuttX requires IOCTL. So I think QuickJS is nice because it's a lot smaller. It's optimized for small memory footprint. And QuickJS supports POSIX. Unlike other full-blown JavaScript engines, if I were to take the whole Chrome JavaScript engine, I think that would take a lot more memory and it won't support POSIX. MicroPython versus Python. Well, my very first experiment was actually with NIM. NIM resembles Python very much, and I like it very much because it's a compiled version, somewhat like MicroPython and Python because of the syntax, but it's compiled. So it's compiled to C, and it integrates very well with NuttX. And in fact, when I started the project, NuttX already supports NIM. So for folks who are keen to experiment with Python, I really recommend NIM. NIM works very well on NuttX, especially on very small devices because it compiles to C and it uses the existing C toolchain. So yeah, so maybe someday I'll look into Python and MicroPython, but that again is going to be a huge thing. MicroPython, as I remember, I tried it on another platform. It's got lots of dependencies. Building it is actually quite tricky. Python again has a lot of runtime memory allocation, so that will be challenging. But anyway, looking for a Python-like language, I strongly recommend NIP.
Okay, thank you, Luke. Any other questions? Okay, now we want some announcements about the boards that we distribute for the participant here. The first board that Alan gave to some contributors, some people that already submit pull request to NuttX, was a NuttX board with the logo. It's based on STM32F401. It was created by my friend Lucas Zampa from Brazil, and that board is really cool because it has many peripherals on that, and that's the board that I use in the YouTube live in the section of tutorials. And so if you guys want to try this board, want to implement things with that, it's already supported in two main lines. So all the features included in the board are there, and even features that are not directly in the board. Like, for example, if you want to use some encoder, like the quadrature encoder, or external SPI Ethernet board module is also integrated, so it's very easy or very fast to prototype with this board actually. And the other board was from the Pine that Loop contact. Correct, Loop? Are you? I think, Loop, can you talk a little bit about this donation?
Oh yeah, sure. So as you know, the work I've done today, I talk about today about NuttX Aux64. All this has already been upstream to NuttX, so you can actually try it today, but you need the board, right? So which is why I asked Pine64 to give us a generous contribution, which is why we managed to secure some Aux64 boards for you to try out. So everything that you see today, you can actually try out based on the text mainline. Yeah. So Alan, I'll leave it to you to allocate the boards to the participants.
Mm-hmm. Thank you, Luke.
Thank you, Luke. The boards have been allocated to people that attended the conference in person due to the difficulty of shipping them. And we hope that next year, when we get more boards from our sponsors, we will have more people in person so that we can handle the boards.
And we also have, thank you, Sony, for the board that will be in the project, in the workshop tomorrow. Yeah, and so, and also for the space, because if we are here, is thanks to Sony to organize the event here in Japan. Of course, it's the other side of the world, and so we know not everybody from other countries are here, but it's important to have this event happen in different countries of the world every year, right?
I think that in 2019, when we started the first event, actually we didn't start it, we followed the example. Dave Maples organized the first one. The idea was, as discussed with Greg, to have one event each year on a different continent. And the first in-person event was in Europe in 19. 2021 and 22 was impossible to have an event, so we had it online, NuttX online workshop now. And 23 was Brazil, so we managed to secure something on the US continent. And this year is Japan, and next year hopefully we will have something in Europe.
Yeah, maybe Europe or other country that is not yet Africa, Australia.
I
I know it's very difficult because I don't think we have many developed in Africa, for example. In Australia, we have some, but who knows? Could be very different.
If we manage to synchronize and everything will be fine, I would really love to have this event hosted under the Apache
yeah.
Con, because that is a big Apache conference. We are an Apache project,
Yeah.
and it would be really nice to show that we belong to the Apache.
Exactly.
So that is my hope, not a promise.
Yeah.
Hopefully we can do it.
Yeah, maybe it could be just after the ApacheCon or in sequence. You want to be in this at the same time?
Yeah, that would be awesome to be in the same venue with every other project.
Yeah.
And then maybe we can meet some of the minute people because they are also under the Apache Foundation. So it will be something to be discussed.
Yeah.
Let's see what the future brings to us. But I think that it's a wonderful community, and
Yeah.
I hope to see more people live next year.
Yeah, me too. So now we have a 15 minutes break, right?
7-ish.
Yeah.
The break is until 30, so we start
Yeah.
again at 30.
Yeah. So, Lupi, so stay wake a little bit more. I think for
Yep,
you
sure.
this time is easy, right?
Yeah, it's afternoon. This is the perfect
Yeah.
time for me.
Yeah. Yeah, you are in Singapore,
Yeah.
right?
Yeah, thank you so much for having this
Thank
in
you
the
for the
Asia time zone.
presentation.
I really miss this. Thank you.
Yeah.
It's fair to have it in each time zone. We will take a 7-minute break and we will be back soon. Thank you very much, Loop. Looking forward to see your next presentation after.
Yeah, thank you. Hello, everybody. I am Lup from sunny Singapore. This presentation will look a little unusual to most NuttX developers. We will do an experimental exploration of NuttX log analysis with a functional programming language called PureScript. If you would like to download the presentation slides, please head over to this link, lutyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation transcript, articles, and source code are available at that link. Today, we can get real-time logs from our NuttX devices like aux64 RISC-V single-board computer and the emulator for aux64 SBC. What if we could analyze the NuttX logs in real time and do this all inside a web browser? Today, we shall explore this with PureScript, the functional programming language. NuttX development can get super challenging. It takes a while to figure out what is really happening inside the NuttX kernel and NuttX apps. Can we improve the NuttX developer experience with functional programming tools like PureScript, or maybe newer hardware? We will chat about this. I promise to stop myself from getting too deep into PureScript. PureScript will feel like listening to jazz music for the very first time. It is interesting. Not 100% sure if everybody will like it, but it is a fun new way to think about the things that we do every day. We are watching a demo of our experimental NuttX log analyzer. Suppose we are testing a NuttX app and it crashes with this horrific crash dump. At the right, something helpful appears. Our log analyzer extracts the RISC-V exception from the NuttX crash dump, and it explains what's causing this RISC-V exception in friendly words, which is great for folks new to RISC-V. But exactly what code caused the crash? Clicking the exception address will show us the NuttX disassembly of the questionable code, which is hyperlinked to the NuttX source code from our GitHub repository. See the stack trace at the right? The stack dump is also helpfully hyperlinked to the NuttX disassembly and the NuttX source code. This will work for NuttX kernel and NuttX apps, with some limitations, of course. Hopefully, our NuttX log analyzer will be super helpful for folks doing NuttX development for the very first time. Now we go inside our experimental log analyzer to understand how PureScript makes sense of all this NuttX crash dump. So what just happened in our demo? NuttX boots on our emulator for Ox64 BL808 single board computer and starts our NuttX app, which happens to be the QuickJS JavaScript interpreter. Our NuttX app crashes with a RISC-V exception. The terminal output shows pages and pages of logs as seen by NuttX developers today. We talk about the Ox64 emulator and QuickJS JavaScript engine in another presentation. Please check out the presentations here. Then our demo shows something totally new. We have a NuttX log parser that shows the RISC-V exception info and explains the RISC-V exception. This is a load page fault. The code at this address tried to access the data at this address, which is invalid. That's why it failed. This was automatically extracted from the pages and pages of crash logs, which is super helpful for folks new to RISC-V platforms. But why did our NuttX app crash? What is the source code leading to the crash? As NuttX developers, we are used to seeing pages and pages of stack dumps. What if there was a way to click an address in a stack dump and jump to a NuttX source code? Yep, we did it. The stack dump is now clickable. Clicking an address in a stack dump brings us to the NuttX disassembly, which links to the NuttX source code. Everything is now point and click. Thanks to the NuttX log parser, we have extracted and interpreted all the interesting bits, the exception info, exception explanation, and stack dump, hyperlink to the NuttX source code to make this really helpful for NuttX developers. This sounds like a dream come true for NuttX developers. How did we make all this happen? What are the limitations and why do this in PureScript? We begin by understanding how our NuttX log parser explains a RISC-V exception by analyzing the NuttX crash dump. In NuttX, we normally see this kind of RISC-V exception. Imagine that I am a fresh new developer coding on a RISC-V board for the very first time. I will probably ask, what exactly MCOS, EPC, MTVal? Well, a seasoned RISC-V developer would say, MCOS is the cause of exception, EPC is the exception program counter, MTVal is the exception value. Not quite so obvious if we are stuck staring at a crash dump. That is why we wrote a script to explain the RISC-V exception in friendly words and in the correct context. We hit a load page fault, our code at this address, tried to access this data address, which is invalid, and it failed. This is how we coded in PureScript. We explain RISC-V exception 13 with this EPC exception program counter and this MTVal exception value. Our PureScript code will concatenate these strings and values together with this double arrow thingy that looks like a diamond. We explain the other RISC-V exceptions the same way. This is how we explain RISC-V exception 12. Yeah, this explanation is still incomplete, but you get the idea. And this is the catch-all that explains all other RISC-V exceptions. All of this looks like a tidy bunch of rules that will explain RISC-V exceptions in a declarative and rules-based way. Looks a bit like makefile or kconfig or prolog. We could have done all this in C or Python or JavaScript, but it probably won't look as neat and tidy. At the top of our pure script function is this thing that looks totally alien. Just think of it as a function declaration in C. This says that explain exception is a function that accepts three parameters, mcos, EPC, mtval, and returns a string that explains the exception. Okay, it looks like we have 4 parameters, but it's actually 3 plus 1 because of the way functions are defined in JavaScript, something called currying. Our demo runs in a web browser with JavaScript. Our explain rules are in PureScript. Can we call PureScript from JavaScript? Yep, this is one of the coolest things of PureScript. Anything we code in PureScript can be called from JavaScript, right inside our web browser. Our PureScript function for explain exception that we saw earlier, it behaves like a typical JavaScript function that we can call directly from our web browser. This is how we call explain exception from JavaScript, passing the exception number, exception program counter, and exception data address. The return exception is returned as a string in JavaScript. All of us have bits of NuttX troubleshooting skills locked away deep inside our brains, like how to read RISC-V exceptions, what the exception means, what causes these exceptions, how we fix them. All these NuttX troubleshooting skills, why don't we express them in code for the NuttX community to execute and reuse? PureScript looks like a neat way to express our troubleshooting skills. Other functional programming languages will probably work too. Ready for a bit more PureScript? This is how we pass and extract the RISC-V exception from the stream of NuttX logs. All of this happens in real time. Earlier we saw PureScript explaining our RISC-V exception. But how did we get the RISC-V exception? The exception cause, exception program counter, exception value? Well, they appear in the NuttX log like this. We wrote a string parser in PureScript to extract the exception info from the NuttX log in real time. PureScript really shines for string parsing, as we shall soon see. Here is our string matching pattern. This pattern will search for the literal string RISC-V exception, skip some spaces, search for literal string exception, skip more spaces, and discard the whole matched string. That is what void means. In functional programming languages like PureScript, we tend to see plenty of brackets or parentheses. That is why we have shortcuts like $. When we write $, something, something, it is actually a shortcut for bracket something, something. So this chunk of code here doesn't need to be wrapped with brackets. A single dollar will do. Next comes a regular expression for string matching. We use this regular expression to match the exception number and return it as the mcos string. Then we skip the comma and we skip more spaces. Finally, we return the interesting bits of exception info, the exception cause, converted from hexadecimal to integer, the exception program counter without the 0 prefix, and the exception value without the 0 prefix. There is a complicated reason why we say this is pure. It has to do with side effects and monads. But we won't go too deep into pure script in this presentation. I promise. One last cute trick in pure script. Sometimes we write back quotes or back ticks like this from maybe. Well, something backtick something is actually equivalent to bracket something something. Okay, enough pure script for today. Hopping on to JavaScript. We have created a string parser in pure script that passes a RISC-V exception. This is how we call the string parser from JavaScript. We pass the exception string to pure script, and we get this JSON result with the exception info. Remember our RISC-V exception explainer from earlier? It works great with our exception parser. Thus, we have a pure script function that extracts the exception info and another pure script function that will accept the exception info and explain it. Once again, how and why are we using pure script? We use pure script to write the rules, to extract the exception info, to explain the exception in a high-level way. We use JavaScript to pass around the nuggets of info in and out of pure script. It feels that we're using pure script to enrich each bit of info with our NuttX troubleshooting skills so that everything makes more sense to NuttX developers. This is how we create a smarter log parser for NuttX. We saw our NuttX troubleshooting skills expressed as high-level rules in pure script, but the rules need raw data and NuttX logs to work on. How do we feed the NuttX logs to the pure script functions in real time? For Aux64, this gets a little easier because we have the Aux64 emulator running inside a web browser, which will let us pass NuttX logs from Aux64 emulator to pure script in real time, line by line. Inside our JavaScript, this is how we pass and explain the NuttX logs by calling pure script. Everything happens inside our web browser, thanks to the seamless integration between JavaScript and pure script. This might become more difficult with other functional programming languages. What about a real NuttX device, like the actual Aux64 single board computer? Well, our web browser can talk to Aux64 serial console directly over the USB serial port thanks to the Web Serial API. The web browser JavaScript that we saw earlier, we could potentially reuse everything and pass the NuttX logs from Aux64 SBC to our pure script log parser. We explained the Web Serial API in the presentation on Aux64 SBC. Check out the presentation here. Here is a quick look at Web Serial API, controlling a real Aux64 SBC from within a web browser. With the Web Serial API, our web browser can talk directly to serial devices connected to our computer, like this Aux64 SBC. Our web browser JavaScript can then send NSH commands to Aux64 and capture the serial output. This is how we might run our NuttX log analyzer with a real NuttX device. One final mystery in our NuttX log parser. How did we hyperlink the stack dump to the NuttX source code? How did we figure out whether a NuttX address points to code, data, BSS heap, or it's just pointing to some random garbage? Again, we have rules for that written in pure script. We match the NuttX addresses with regular expressions. This rule says that 502 something something comes from NuttX kernel code. This rule says that 800 something something comes from NuttX app code. We make the distinction between NuttX kernel and NuttX app because we need to hyperlink to the correct source code. Everything else points to random garbage. We won't hyperlink to the source code. This is how our JavaScript calls pure script to match a NuttX address and figure out whether it points to NuttX kernel code, NuttX app code, or just random hot garbage. Okay, it is a little disturbing that we are hard coding address patterns for this demo. Our troubleshooting rules might evolve. Depends how folks will use our NuttX log parser. The address patterns will be different from RISC-V and ARM platforms. How will we customize the address patterns? That is why we have an online pure script compiler that will allow troubleshooting rules to be tweaked and tested easily across all NuttX platforms. What exactly is this online pure script compiler? How will it compile the troubleshooting rules for our NuttX log analyzer? Let us take a peek. Remember the rules that will identify an address, whether it is kernel or app? The rules are located at the left in our online pure script compiler. And we tweak the rule that will identify an address. Notice that the results are immediately reflected at the right side. This will make it simpler to create and maintain the NuttX troubleshooting rules in our log analyzer. The next part of our NuttX log parser will be helpful for folks who work with NuttX disassembly. Given a NuttX address like this, how do we show the NuttX disassembly? Our solution is to chunk up the NuttX disassembly into many small files grouped by NuttX address. So this NuttX address will appear in this NuttX disassembly file, which gets hyperlinked into our NuttX log display whenever this address is displayed. How do we split a NuttX disassembly into smaller chunk files? We begin with the ELF executables for NuttX kernel and NuttX apps. And we export the RISC-V disassembly into a file like this, qjs.s. We wrote a NuttX disassembly chunker in Rust that will take a huge NuttX disassembly like qjs.s and split it into smaller disassembly chunk files that are grouped by NuttX address. So this disassembly address goes into this chunk file and so on. This is how we're able to render the NuttX disassembly for any NuttX address. This works because we have disassembly files in small chunks that we have loaded into our web server. What about hyperlinking to the NuttX source code? Inside the NuttX disassembly, we have the path name and the line number of the source code. Our JavaScript will convert these into a hyperlink that will jump into the line of source code in the NuttX GitHub repository. All this will save us lots of time. No more searching and grabbing for the NuttX source code. Just click and the source code appears. Back to our original NuttX horror story. We ran this NuttX app and triggered this strange NuttX crash dump. that looped forever. What caused this strange problem? This was before we created the NuttX log parser. We had to search and grab for every single NuttX address that appears in the NuttX crash dump. Jumping from NuttX disassembly to NuttX source code again and again and again. It took us a while to realize that this crash could never possibly happen. There was a clear sign that we missed, the loopy crash dump, which means that the NuttX stack was full. This is why we need a smarter log parser that will catch these common problems and prevent NuttX developers from falling into these traps. And that is all for our experimental log parser. Given real-time logs from a NuttX emulator or a NuttX device, it extracts the exception info and explains the exception. It produces the clickable stack dump that links to the NuttX disassembly, which links to the NuttX source code. The NuttX troubleshooting rules are still evolving, so we have an online compiler that will compile our NuttX rules and run them inside our log parser. Okay, thanks, but why are we doing all this? Why are we making a smarty pants log analyzer for NuttX? Why are we doing rules-based programming with functional programming languages like PureScript? Who are we really trying to help? Well, we're doing all this for NuttX developers, of course. We wrap up our presentation today by reflecting on the NuttX developer experience, lessons that we have learned from Aux64 single board computer, and why we are hopping sideways to a newer single board computer, Softgo SG2000 and Milk 5 Duo S. I think NuttX on Aux64 has been somewhat successful. At least I see some folks using it. What is it about Aux64 that makes it appealing to NuttX developers? I have a few hypotheses. I think RISC-V 64-bit might be easier to learn, which is great because we will see many RISC-V boards based on the RISC-V CPU, T-Head C906 CPU. Aux64 SBC is highly affordable at $8, so that helps. Though looking back at Aux64, I would have preferred a $10 board with an Ethernet port, so we don't swap the microSD so often. We will talk about SG2000 in a while. Embedded development seems to be moving away from plain old OpenOCD and GDB, like my good old days with STM32 Blue Pill. Today, we are working with RISC-V SBCs with network booting over TFTP, plus a NuttX log analyzer that runs in a web browser and links to the NuttX source code. Our development machines are getting more powerful. Today, we can run Aux64 emulator on our computers and complete the OS test in seconds. Could this be a sea change in the way we do NuttX development? If you're looking for a more powerful RISC-V board, check out the CanMV K230 based on the Kendrite K230 SoC, which runs on T-Head C908 CPU, which is the upsized version of Aux64 and T-Head C906 CPU. My good friend YF has been super successful with the porting of NuttX to the Kendrite K230 SoC. Maybe someday we can use the onboard camera and run some image recognition apps directly from NuttX. Porting NuttX to K230 was an interesting experience. YF is based in China, I am in Singapore. Very often we would stare at the NuttX crash dumps and figure out what went wrong. There's so much NuttX expertise locked away deep inside my brains. I feel kind of bad that I couldn't share my brains with YF and make the NuttX porting a little easier. This is my motivation for creating the NuttX log analyzer that I presented today. Now we head back down to a cheaper $10 board, the Milk 5 Duo S, based on the Softgo SG2000 SoC. We expect plenty of new SPCs to be released soon, with the Softgo SG2000 SoC inside. That is why I ported NuttX to SG2000. This is a $10 board with Ethernet port, which will put NuttX over the network. No more swapping micro SD cards again and again and again. The pins are all exposed, no soldering needed, easy to attach sensors and actuators. Reminds me of Arduino Uno actually. There is a more powerful SG2002 SoC that comes with a smarter tensor processing unit, which might work better for image recognition. This board comes with a MIPI CSI input for digital cameras. I am now upstreaming NuttX for SG2000, and I am building the NuttX emulator for SG2000. All the nice things we've learned for aux64 SBC, we're doing the exact same things for SG2000. Check out the details in the article here. Here is a sneak peek of NuttX booting on an SG2000 SBC, the Milk 5 Duo S. This is a $10 SBC with an Ethernet port. So we see our SBC booting NuttX over the network with TFTP. No more swapping of micro SD cards. I highly recommend booting NuttX over the network with U-Boot bootloader. It makes NuttX kernel development so much quicker. We conclude today's presentation with LLMs, large language models. Can they help with NuttX troubleshooting? Today, I use the RISC-V disassembly of NuttX kernel for troubleshooting all kinds of problems because the NuttX disassembly has everything inside. Who calls what, macros all fully expanded with links to the source code, like we saw in the presentation today. But the NuttX disassembly has way too many details inside for human brains to ingest. Maybe an artificial brain will help. So we politely ask the AI, here is my enormous NuttX disassembly file. Please digest it and answer my question. How will the NuttX boot code start our NHH shell? Tell me very precisely, step by step, what happens exactly when NuttX boots on my device all the way to NHH shell. Here is the answer from a popular LLM. It looks promising. It seems to know something about NuttX booting on RISC-V devices. Or maybe LLM is just regurgitating my NuttX articles. For folks who can't distinguish LLM from MLM, no worries. We will let you know when this stuff is mature enough for daily use. If you are keen to learn more about PureScript or try out the new port of NuttX to Softgo SG2000, please check out the articles here. We have two more presentations on aux64 SBC about porting NuttX to aux64 SBC and the TinyEmu emulator for aux64. Please check out the presentations at this link. Today, we took real-time logs from an emulated NuttX device and did some real-time analysis. It looks feasible, though we might take a while to capture and record our NuttX troubleshooting skills to make the log analysis truly helpful. Now is probably a good time to think about the NuttX developer experience. Can we make it better with functional programming tools like PureScript or newer hardware like RISC-V SBCs? Let us work together to make things a little easier for new NuttX developers. Thank you. Yeah, thank you for watching my presentation, which is on a rather strange topic. Are there any questions?
Hello. Let's see here if we have some questions from audience. Anyone has some question about this uh, last presentation from Loop? No? Let's see here in YouTube. Okay, Loop, seems like no one has some questions. So I think uh, we can thank you for your presentation. It's really nice, really good presentation. And actually, maybe Alin or I can ask something um, very simple related to that. So, what your opinion about these artificial intelligence artificial intelligence systems? Do you think it's possible to eventually replace us as developers to simplify programming, or do you think we are too far away from that?
I'm not sure. Yeah. So can artificial intelligence actually help new developers? Is something that I'm also very curious. So the thing is that you and I, we are not beginners. So therefore, we are not the right person to test this. So actually, one of my goals for the Google Summer of Code and my student Rushabh, we'll try and see whether AI can actually help. Maybe we'll try using some LLM to actually try and explain some difficult code in NuttX, or maybe even try to tweak some parts of Rust so that it works correctly. So maybe we'll document the results and we'll see why. But yeah, but overall, I'm a bit pessimistic. So my main concern with these LMs is that it requires a lot of energy, a lot of data, a lot of huge data centers, a lot of water to cool them. So it's not very eco-friendly. So I'm not so sure we should actually use these things unless they're really that powerful and they really work that well. So maybe through our experiments in the next 3 months, we'll find out whether it's really worth it to use this LLM. Otherwise, it's all just a waste of energy
Yeah,
and environmental resources. Yeah.
yeah, nice. And yeah, maybe it could be also used to help to create documentation based on the source code and so on. It it's some it could be useful for some tedious work like that, right?
Yeah. Absolutely.
Okay. Thank you, Luke. Thank you
Thank you.
for
Thank you.
great job. I think next presentation from Alexis. I see uh, he in Jitsi. Hello, Alex. Alexis, can you read? Can you listen us, or you still? Okay. Ah, see,
Hello,
you are here,
you hear me?
Alex.
Yeah,
Hello, nice,
I
clearly.
I guess
Yeah.
we're a little bit ahead of schedule.
Yeah, if you want to presentate now, it should be nice because we can finish early here. So,
All right. I just had one note I wanted to add, but I'm gonna say that at the end. Yeah. Please give me 1 second, and I'll get the slides ready. I'll be ready in 60 seconds.
right, take your
Sure.
time.
In the meantime, we will display the schedule for today, and I will do the necessary preparations for the room to be able to watch your presentation. Thank you very much for being today with us.
Line. Hi, everybody. My name is Alexis Christoforidis. I am the team lead over at Wilderness Labs for the MetaOS project. And we're going to talk about that and the Meadow platform today. It is a .NET IoT platform based on NuttX and the STM32 F7. So let's talk a little bit about us. We are a small team of electrical software and embedded firmware engineers and visionaries trying to.
Alex,
Hello?
Alex, I will ask you to stop a little bit.
Slower? Alex, it's a problem with video
I will
audio.
ask you to stop a little bit.
Slower?
No, there's some microphone open.
Line. All right. Hi, everyone. Take two. My name is Alexis Christoforidis from Wilderness Labs. And I'm here to talk about MetaOS and the Meta platform. It is a .NET and NuttX-based IoT platform. And real quick about Wilderness Labs, we are a small company of electrical software and embedded firmware engineers and some people who have become engineers just by imagining what we can do with this. We have our mission is secure and scalable IoT, and we have always had sort of a vision to do this through .NET and a very robust kernel and a system based around that core. So about me, we're gonna skip most of that, honestly. But the important part is that I have worked as a .NET runtime engineer at Xamarin and Microsoft. Xamarin being a startup where .NET was brought into small platforms, such as smaller for embedded, not small, but smaller than desktop, which is to say Android and iOS, Apple Watch devices, and even some video game consoles. The Meadow IoT platform is going back from .NET, has some basic principles that we're trying to bring to everyone. And the major one is modern software development. We all know that that's not really a thing in IoT unless you go all the way to Raspberry Pi. And by modern software development, we mean rapid software development, memory and type safe mobile development, bounce checking, etc. A modern compiler that works with you, and modern syntax and composability in the type system. Things that we don't always have down when working in C, like most of us, you and I. But we want to not necessarily abstract, but safely wrap that around in a managed and safe, memory safe language, so that applications can be written rapidly and safely, just as they can for other computer platforms. We want seamless internet security and over-the-air updates as part of our platform. And we consider, of course, as basic principles that the IoT platform is reliable and recoverable in the field. If it's going to be the core of a variety of many devices, the OS needs to be reliable, recoverable, does not, from hardware watchdogs to recoverability and crash reporting. And finally, we are aiming to provide fleet management to all the IoT devices, whatever form they may take. Meadow Cloud is the endpoint for the information from heartbeat and health reporting to command and control, sending down commands to the IoT device safely, to data being streamed up from sensor modules, etc. This is a Meadow in hardware. It is an actual device. We've sold thousands of these. They are used by many of our clients who are prototyping or field testing IoT devices based on it. We have the Feather form, classic for prototyping and being able to plug in. The form factor allows you to just sort of plug in on and work with a similar Feather peripherals. We also have the compute module, our smallest form factor for the Meadow. Real basic here. We're not gonna get too much into this, but it's most people here know the STM32F7. About a 200 megahertz ARM thumb 2 CPU, and the Meadow also has a network processor, the ESP32, and I forgot to put the model there, S3, I think. Anyway, 32 megabytes of external RAM in a chip and 64 megabytes of persistent flash for file system and the app itself. Really quick, we split Meadow OS into a lower half and a higher half, and sort of like it's mostly to understand the platform. But at the lower half, we have the NuttX kernel. We have our bootloader that handles updating the binary, the OS binary itself, as part of the OTA process. And we have one module of ours called HCOM, which provides USB def connection, provisioning, and debugging. On the other hand, we have the higher half, which is Mono, and which is a .NET runtime. We'll talk about this in a little bit. And also our Wilderness Labs libraries, Meadow.core and Meadow.foundation, that we are going to talk about more in a bit also. And of course, Embed TLS, which we'll also kind of briefly talk about, but that's just a standard TLS library for NuttX implementing internet security. So the Meadow OS lower half, again, the bootloader, as we said, is mostly to just start the NuttX kernel or otherwise replace it with properly staged update and perform rollback, etc. if the update is unsuccessful. And the NuttX kernel is the main kernel for the Meadow OS platform. It's the first thing that boots. It's after the bootloader, and provides all the lower level capabilities for the OS, from, of course, memory allocator and scheduler to TCP/IP and some of our network drivers, and all the STM32 peripherals, of course, and like the RNG, etc. So we are very much have NuttX on our core. But moving on from then on, things get a little bit different from the usual NuttX model, and I'll explain in a bit. Next up is ESP32 comms. The ESP32 chip provides Wi-Fi and Bluetooth for us, as well as, I forgot to put this here, but this is where we put our key pair to keep it away from the user app processor. So we use it for encrypted secret storage. But this is a whole component that our firmware engineer, Mark Stevens, and Wilderness Labs veteran has written. I forgot to link it here, but I will link it afterwards because he's already presented on this. We're not going to get also too deep into this. So I basically wanted to link into his fantastic presentation about how he built the bridge between ESP32 and the STM32 for providing a user sockif driver for Wi-Fi. HCOM is the next component, which is USB connection. That's how we put things on the device, how we provision the device, and a few messages such as provision, write file, read file, device info, and how we build a USB channel through which .NET debugging commands flow through, and that's how we have .NET debugging. OS and app updater, what it says on the box, and the rest of the lower half is us pretty much exposing a lot of low-level functionality to user space. Now, going to the higher half where these things get interesting, we have Mono, which is a .NET app, which is our .NET app runtime. Metal Core, which provides an I/O API, app lifecycle management, and over there update management. Metal Foundation, it's a peripheral layer and platform utility code. And finally, Metal Cloud Daemon provides health reporting and push updates. What is Mono? It's new for a lot of you, but it is an open source .NET runtime, and one that has a long pedigree for portability. It has an interpreted mode, anything from an interpreted mode to ahead of time compilation mode in LLVM. So it kind of runs the gamut when it comes to performance characteristics of generated code. It can be ported in quite a variety of platforms, from WebAssembly to the Sony PlayStation on a game or two, to PowerPC and many others. And it is actively developed by Microsoft and kept to the latest .NET version. And that is a project that we took a lot of use out of. It is, in essence, the other half of our platform. If we want to talk about just two components, it's NuttX and Mono. And here we go. Mono and NuttX, in general, was an easy thing to put together. It only took a year or two or three to sort of work properly. Mono had to be tweaked for having a small binary in order to fit. We didn't even manage to fit in internal flash for the STM32, so we wrote some code to break it apart and have into external flash. So it's about 2 megabytes, but we managed to get the RAM footprint pretty low for .NET. We found small differences in how NuttX implements POSIX versus the most popular POSIX-ish operating system that Mono supports, that is Linux. But sort of once understood, it was just a matter of adding another if-def in Mono to support one more operating system, as it is used to having. We had to add support for nested POSIX signals, as signals are used by the garbage collector in Mono to stop threads and create a stop the world garbage collection environment. And we had to add that. I'm not sure if this is upstream, but please let me know after the presentation if there's any interested in that code or what you think about that. We had to use a cooperative GC thread suspend. We basically have to make sure we don't suspend a thread while it is in malloc, because in other systems, Mono can uses kind of cheats and uses malloc and mmap as two ways to do allocation that are not gonna deadlock if you accidentally suspend one or grab a lock that one needs. So basically, we had to make sure our threads tell each other when they stop at checkpoints and wait until all threads have stopped, and then a GC occurs. Instead of positive signals being sent to threads in order to suspend them. It is a more robust thread suspend way anyway, if slightly slower. We switched to round robin scheduler for .NET threads. .NET system is the .NET system is non-deterministic in thread scheduling behavior, or rather, I should say, it does not expect its threads to be in a real-time system where priority actually sort of matters more than softly. So in .NET, things can be initialized by any thread. So a high-level thread could be waiting for a low-level thread to initialize a type. And in .NET, in .desktop, that was always going to work. Here on FIFO, proper real-time scheduling, we're not going to see that. We're just going to deadlock as a lot of the times we had like tight loops and for initializing components in Mono. Finally, the app is loaded. Once Mono is loaded in the OS, the app is loaded from the Flash file system. It's just a DLL. If you don't know, .NET files compile into DLLs. And here's a big difference from other NuttX systems. So oftentimes, Mono plus HCOM for developer stuff is the entire user space. So from now on, the user is just accessing all of the system through the app.dll. So all of this just to get to console.writeline hello world. Not very impressive, but you're starting to get the picture that we're gonna be writing code within C# and .NET as much as possible. Another addition that we did here is this is all Neil Ferguson. Some of you may know him. He's a star. He's a little bit of a legend in porting Mono to different platforms. But Mono had support for ARM and ARM CodeGen, but not Thumb2 only CodeGen. It had some Thumb2 support, and now we have full Thumb2 support thanks to Neil Ferguson. The just-in-time native code generator in Mono works really fast and generates okay native code, which is in JIT compilers. This is sort of a pretty okay compromise. You don't want a slow compiler in something that is on device. That's just gonna take a while to just get an app started. And that gives us an increase over interpreter speeds as we are basically native code, if not that optimized. Mono plus embed TLS, that's some more work we had to do. Embed TLS is pretty standard for NuttX. We understand now even more as it is part of the repo, but it wasn't so for Mono. It was never really made for embedded. So we made embed TLS provider and added a root PEM store, and with this together, you can execute code that very seamlessly uses TLS. That's how .NET does it. You just put HTTPS in your HTTP client URL that you want to reach, and it's just going to work as it would with HTTP. And then we have we have Mono as NuttX user space through Metal Core. We expose as much of NuttX low-level feature functionality as possible through system calls and ioctl operations. We're migrating to just system calls, but just historically right now we still have ioctls. So we are creating bindings in .NET because .NET interoperates with C code very easily and efficiently for doing all kinds of serial protocol communication, power management, connecting and disconnecting Wi-Fi, receiving Wi-Fi events, scanning for networks. We are bringing all of this into C#. So, oh, that's the wrong thing here. But we provide this as a way for people to access low-level features while going through a safe wrapper, safe through the .NET language of type safety, memory safety, and bounds checking that it uses, but also using wrapper code in order to make this as a delightful experience as possible and make sure things are not accidentally abused. But basically, we have direct programmatic access of the STM32, and through that we have a whole peripheral ecosystem of over 300 devices, from geolocation to displays to cameras to sensors, tons of utility code for working with these displays and sensors, and all of this along with Metal Core is open source, and very easy to add to your platform, very easy to modify similar drivers to adjust it to similar devices, and heavily tested. So all of this is already part of the platform. And finally, we have work that Neil Ferguson again did in NuttX and has recently been merged. This unblocked us from using DLOpen and DLSim on the STM32, which allows code like the code over here below of just loading a dynamic library linked against linked against MetaOS and its libc, and then just calling it. So we have used it to get TensorFlow on MetaOS, and I'm working to get libjpeg and other standard libraries. And as soon as we build them, using them from Mono is direct. In fact, many of these libraries already have .NET bindings. So oftentimes it's just a matter of getting a build, and then people can use just C# without writing anything more. Future of MetaOS, there's a lot that we are excited about to do that are working on the OS itself. But from the NuttX perspective, we are very excited to get to the latest NuttX. We are way behind because we are still on NuttX since we started building MetaOS back in 2019, I believe. And that was before I joined the team. The effort is underway and we got it to boot. And we need to put Mono on it and see if that runs, is where we are. There were many small challenges with basically with reporting some things. A lot of our custom kernel code, especially for the ESP, had to be tweaked as internal structures for networking have changed considerably. But in general, we're excited about CAN bus support in latest NuttX. I'm not sure exactly when it was added, but it was not in 7. I2S for audio, which Alan has recently helped get on the latest MetaOS, but not we couldn't get it back to 7.3. And similarly to that upgrade, we need to upgrade our other major component, Mono. It is also kind of in 2019. Again, very robust, and the .NET Standard 2.1 is a long-term target for .NET libraries. So there's a lot of surface here, but we want to be future-proof, and recent .NET is even faster, more memory efficient than what we're using. So we are, of course, excited to get to that. And really, as a pipe dream, maybe even a personal pipe dream, realtime.net is something that we would love to bring to the .NET world. It would mean a lot of changes in both how we think about .NET, as it's never been a real-time system, but a subset of it can be. So the concept of a .NET or a .NET thread not using a heap, and under other limitations, can execute some code in real time in isolation. And that way we'll be able to actually provide that feature of NuttX to the .NET world. As I hope it was clear from before, we're not trying to be a platform for real-time apps, as .NET is not real-time. If we're going to do that, we have to change .NET itself. So big goal, have to convince a big company named Microsoft, but we like to be ambitious. Thank you so much to the Wilderness Labs team, everyone from the MetaOS team to the founders, anyone in between. Thank you so much for making what we did possible, and for all of us, for all of the team for continuing to work on this through many years to get to the point where we are today. Thanks to the Apache Foundation for this workshop, and the NuttX community for supporting MetaOS in PRs, open source contributions, comments, etc. We'd love to know more of you. Many of you that we already know, we love. NuttX is a great project, and we are happy to be part of it, even as just users. Thank you. Thank you very much. Are there any questions? I guess I should ask here. If there's, I'm not sure if I have someone of an in-between who can tell me if we have questions on YouTube.
Thank you, Alexis. Actually, we have a question from Tomek. He is asking, you told the C#.NET is safe and secure, and he's asking how it compares to Rust, that claimed to be the most secured language of the world.
It's
at least I think you can defend the code quality, right? Because for a human to learn Rust is not that easy.
Yeah, this is a very good argument, and I am not gonna talk badly about Rust. Rust, however, is not currently a rapid application development language. It takes very long time to prototype things. It's also like a little bit behind on embedded. So if Rust gets better when you say APIs, etc., then yeah, that is a good language to use for Meadow. In fact, I tried to leave it vague in the beginning versus .NET because our CEO, Brian Kostanich's vision for Meadow is that it doesn't have to be .NET. It can be any any modern language that provides type safety and memory safety and bounds checking, etc. And Rust can be definitely more efficient than putting a runtime. However, in safety, they are about the same. Rust solves the issue in a very powerful way with the borrow checker, whereas .NET uses a garbage collector that sweeps in at different times. Rust's approach, when done right, is probably much better for real-time applications. .NET, however, has also moved away from using the heap for a lot of its work and can work with either spans on working with span times on stack, etc. So direction that .NET has been taking is zero allocation or low allocation applications, and that's where you get Rust similar to Rust's behavior. They are, but in the sense of the guarantees that they provide, they are similar. They are both are memory safe. Both do not allow you to improperly abuse memory, and both allow you to do it if you type a few magic keywords, because you sometimes have to. But yeah, Rust is definitely something that could be a Meadow platform target. However, yeah, .NET is our current one and the one that we're putting the most effort into. Thank you for the question.
Thank you. I think it's a good explanation. Some question from our local audience here. Question? Seems no question here. So, Alex, thank you very much for your time. I know it's not easy to wake up 5 a.m. just to be here with us. And thank you for your great work with NuttX and Meadow, and to be a good help and support to NuttX.
Thank you, everyone, in the NuttX community for your work. I would love to find a way to chat with you afterward, but also within an hour, yeah, I might crash. It is very late/early here, but thanks, everyone.
Thank you very much for the effort.
Yeah, it was really nice and really great presentation. And yeah, I think we can have more integration in our community, right? To also, for example, to have more NuttX things in the Meadow event, and also more .NET Meadow in our NuttX events. I think with this, we have the third presentation, because Mark presented in the past about the Wi-Fi ESP32 integration in Meadow, and also Neil present about the ELF dynamic loader that was implemented to Meadow and integrated on NuttX. And now you're contributing overview what is Meadow. Yeah.
Yeah, I gave more of an overview.
Here's the picture.
Yeah, it's you've seen parts of it before, and I think it would be very useful to link to those presentations for Neil and Mark's work. So if there's a chat for everyone online, let's I'll send the links here and can put those on.
Yeah, and just one question, because I also have some, I don't know too much about .NET, but for example, you can just load the dynamic library and use the function, right? The native functions, correct?
Yeah, you just have to match the signature so that it's correct, and then you just call them. And .NET auto generates marshalling code between C and .NET. So
yeah, so it is similar to Java GNI, right? Java native interface.
yeah,
To
I forget.
call C function or.
It's been a while
Mhm.
since I did GNI, but it's very going back to, I don't know if you can still see the slides, but this little snippet is all you need basically, and then that function is implemented basically from the aspect of .NET. So there's now a function called tflight
Yeah.
microinterpreter invoke, and you don't need to do anything else. Just you need that attribute that says DLL import. So it gets the name of it finds the name of the symbol because it matches the name of the method. So there's a little bit of magic going on there. But .NET is really good at interoperating with C. It's very, very seamless. So allows this binding of native libraries for things that are too intensive to do in .NET, or standard libraries such as TensorFlow and libjpeg can just be loaded and used.
Mm-hmm. Nice. A question about it is that the only way to load? Imagine I don't want to load external library. I just want to compile C code and integrate directly. There is some other alternative, or it needs to be a library and loaded that way.
Yeah, the OS platform is always C# and .NET centric. So I guess that's the part where I meant this is the whole user space. If you want to run C code, it's going to be a component of your C# code. Always the C# code starts first, which is counterintuitive,
Right.
but all of the startup code and a lot of the OS code is in Meta Core and Meta Foundation. And you just then call the C code.
Okay, perfect. Thank you very much again, Alex, and thank you for being here.
Thanks, everyone.
Thank you.
Nice to see you, and have a good day.
Thanks.
Thank you.
You too. Bye.
And I hope to see you in person here next event.
Bye.
I hope so too. I really do.
And with this last
Thank you.
Thank you. With this last presentation, we close the day for today. Thank you for all attendees that came here and lasted from morning until now. It was a quite long day. Tomorrow morning, we start with the workshop. First presence in person at 8 a.m. for the ones that receive the board, and the others can come from 10 a.m. So be here 9:45 so that we can handle badges and you have enough time to get a seat. For the online attendees, if you want to watch us doing the presence workshop tomorrow, you can attend the stream. We will have a live stream, but it will not be interactive. So we will just have the camera up and running, and the conference starts from 10 a.m. Japan time. Thank you very much for attending online and for attending in person. We want to close the day, and we hope to see you tomorrow. Bye.